Come stai, Filippo?
Dai, un po' stanco della situazione, ma insomma, spero di riuscire a rientrare in Italia per l'estate.
Sei vaccinato?
No, non sono abbastanza indietro qui con i vaccini, quindi non siamo vaccinati.
Quindi no.
No. So I think we can almost start this section, which is the 9th section of IGF. And it is my pleasure to introduce Professor Rao, the honorary president of IGF, for this that is with the title Plastic in the Condition of Poor Shear, a Fundamental Instability. So thank you, Professor Firrao, for this presentation. The floor is yours. Thank you so much.
Thank you, Chairman. Thank you, everybody, for being here, ladies and gentlemen, especially those who yesterday night enjoyed a very good reception and a fish-style dinner. And we clapped once more our current and soon past president, Professor Iacoviello. Well, without too much ado, let's go directly to the topic, which is plastic instability in the condition of pure shear, which is a fundamental instability of materials. What is plastic instability? It is a phenomenon of localization of a plastic flow, when the general flow, while we are testing a specimen or when we are loading a structure, becomes localized at some critical condition. We know for sure one of the two types of plastic instability, which is diffuse localization, like in the case of necking of a cylindrical tensile specimen. And we know that from the considered construction, the condition of onset of necking is given by the relationship, the sigma and the epsilon equals sigma. We are always speaking of true stress in this environment. The second type, which is less known, is the localized plastic instability in narrow bands, as in the shearing instability, which are happening in the direction of zero extensional strain. This is the link between pure shear, because there is no strain in the opposite direction, and the material on either side of this band of localized deformation becomes rigid and no longer are in a state of flow. When do we encounter this instability? While we are testing sheet specimens of high-strength steels or aluminum alloys or high-strength aluminum alloys, which are alloys with a very low strain hardening exponent. Please note that when we are in plane stress, necking is not excluded, but the angle with the transverse stress direction is about 33 degrees. Theoretical computation for uniaxial state of stress gives 35 degrees and 16 minutes. And now we see a series of this type of instabilities in a series of AISI 4340 steel sheet specimen that are 1.14 millimeter thick and 7.72 millimeter wide in the gauge section. And this steel has been quenched and tempered at various temperatures. Here you see what happens at the tempering temperature of 510 degrees C. I was doing this experiment in the States, so it was 950 degrees Fahrenheit. And these are the succession of the loading condition with the loading is increasing. And you see that there is a band of localized deformation that forms, and just before fracture, you see that the inferior part moves in opposite direction than the upper part up to fracture. And then we have the same type of specimen quenched and tempered at 800 degrees Fahrenheit, 427 degrees C, and we see the same phenomenon and the same movement of one part in respect of the other, and the angle here is about 32 degrees. 700 degrees C, the situation is just the same. You see the localization just after reaching the yield stress that becomes more pronounced up to fracture. And this is the final situation when the specimen is quenched and tempered at a very low temperature, 600 degrees Fahrenheit, 316 degrees C. The school in which I was working was making a lot of consideration and a lot of experiments. And you can see that while you change the width to thickness ratio, which was done by keeping the width the same and having different specimens with a lower and lower thickness, the angle, the orientation in the instability band at fracture decreases, and in the stress ratio goes to a lower values, is the ratio between the sigma 1 and the sigma 2. And here you see that when the specimen is, let me say, thick, about 1 millimeter thickness, there is necking because that is not excluded. There are two different bands that form at the beginning. Why there are two? Because the probability of having one or the other is exactly the same, and calculation give you exactly the same probability. And then you have on this specimen in which a grid was impressed before testing the final fracture. And here the angle at initiation is higher and then falls at 28 degrees point something, 0.8, when you reach the fracture situation. If you are increasing the sigma 1 to sigma 2 ratio by reducing the thickness to a 0.33 millimeter value, you see that the concentration of deformation within the band becomes less and more pronounced, and you clearly see the movement of the two rigid parts up and down in respect to the fracture that signal the movement, signal the sliding of the two parts, one in respect to the other, in a very sensible way. So there is a continuity before fracture, a continuity of material in the vertical direction, longitudinal direction, but there is a variation in the tangential velocity, and so that is the reason of this movement, as it is represented in this view graph, in which you see the slip line, the continuity condition in the direction perpendicular to the slip line, and the variation of the tangential velocity of the two parts, Vt0 and Vt1, and delta Vtt is the tangential velocity discontinuity. What causes the formation of this discontinuity in tangential deformation? The attainment of an ideal plastic state of the body that can be preceded by an elastic deformation before or no deformation in the classical approach, rigid ideal plastic. And there is no increase of the flow stress during plastic deformation because there is no capacity of strain hardening. And therefore, also in fatigue, you don't have any work that is consumed because there is no work hardening, no rise of the flow stress. This situation has been studied, and if you speak in terms of true stress, you know that the true stress is controlled by many parameters: the strain rate, the temperature, the metallurgical structure of the material, and also the surface energy. And if we go to the differential, you have this expression in which you can reason that, okay, we don't have an exact differential, but if we consider 2 points of the loading story that are not far apart one from the other, then you can think that there is no significant variation of the metallurgical structure. There is no variation of the surface energy, and so the equation above restricts to the one here down. If this delta sigma goes to 0 or less than 0, then you are attaining the situation of the possibility of activation of a tangential velocity discontinuity. For those of you that are interested in the mathematical derivation, here are all the possible works on mathematics, but let's go to the fundamental. If the strain hardening exponent is low and goes to 0, really, and also the variation of strengthening by strain rate hardening, if the M, which is the exponent of the strain rate hardening, is low, everything restricts to this term, and since we have adiabatic heating, then the whole goes to a value less than 0. And a real material can attain the situation of a localization of plastic strain in a direction of pure shear as soon as it simulates a dynamic, ideal plastic flow. And if you go to study better the parameters that are pertaining to this EC43 steel, which is, by the way, equivalent to a 40 nickel chromium molybdenum 7 in European terms. And this is the max composition if you are mass percentage composition, if you are more prone to know completely what's the steel, you see that the value of M hardening by strain rate hardening or softening, because sometimes you have softening, these values are very low, and also the values of N at various tempering temperature. So in a great range of ultimate tensile strengths of yield strength, also N is low. So this is a steel that is really capable of attaining something that we can define as a quasi-ideal plastic state material. And if you go to test various, a couple, we did a lot of tests, through stress, through strain, you see that you reach a situation of maximum stress, which we are not really accustomed to see in the true stress, true strain curves. This specimen was quenched and tempered at 482 degrees C, 900 degrees Fahrenheit degrees. Now, if we go from the tensile specimens to bend test of Charpy B-type specimens, we have a similar condition at the root of the notch. This specimen is in the situation of S quenched from 870 degrees C. This is a section of the specimen. This is the root of the notch. You think of a Charpy type specimen with very notch root radii, but in this case, obviously, there is only one and quite large. Initiation happens at some distance from the notch center line and develops along lines of slip up to the center line, where then it goes to a usual fracture that in this case was a ductile one. In the case of other type of material, you may have brittle ones. But here a slip along this line. This situation was independently assessed by George Krauss, and you see the specimen is not 4340, is 4130, which means that you don't have the nickel and you have less carbon, and this is the notch of a CVN specimen, and this is the point of initiation, which is far from the notch center line, and this is the slip along this type of localized band. And Krauss further speculates that there is a value of beta of the angle at which there is an initiation, and then there is a propagation along one of these slip lines. This is the strong instability, but think that there are movements along all of these lines. So the farther is the point of initiation, the larger of the volume in which there is energy absorption. And then you can see that the farther is the point, the higher will be the J1C, K1C of this material. And here you can see a representation of the fact that in the same specimen you may have slip along a slip surface, or a slip along another of these slip surfaces, because as I was telling you, one or the other, they are completely equivalent in terms of solution of the continuum plasticity material. Here is another view with another specimen in which the notch is upside down in respect to the previous fracture, and you can see the slip surfaces along which there was this concentration of deformation. By taking a very large notched bend specimen, it was possible to see the point of initiation. And you can see that along this slip direction, there is a tangential velocity discontinuity with one piece of the material sliding in respect to the other. If you take specimens with different notch root radii, you have clearly the situation of the slip surface in a situation of pure shear. And you can see that this is a 4340 still in the sequential condition, that the beginning is characterized by situation of many cracks developing. So there is really, before going into the slip line field, a situation with the annulus completely free of stress because of the multiple cracks that you have here. And this is the representation with this stress-free zone, and then the stress, the slip line field goes after, develops after the formation of these stress-free annulus. What I wanted to show you is that the complete independence of this type of fracture along slip lines in respect to the situation that you have before. You may have the formation, the initiation of formation of pores around second phase particles, but then as soon as the condition for the activation of this tangential velocity discontinuity, you have that the shear cuts across, and you see this type of pore which are elongated. One more thing, and then I will stop. We can see shearing instability in pore collections, and you have, if you have copper, which is a very ductile material, you will have pore collections by continuing plastic flow and reduction of this ligament, or you may have disactivation of shearing instability. I thank you for your attention, and I hope that as up to now, the conference of the Italian group on fracture will go on successfully.
Thank you so much, Professor Firra. We have time for a question or two questions. So if the audience have questions, we can proceed. Is anyone from the audience that have questions? Please. So I would like to ask a curiosity about your very good, very nice presentation. It's only a curiosity. I'm not an expert of this, but can you give a bit more explanation about the triaxiality effect close to the notch? Because really that that can be important.
When you have the notch, you have obviously a triaxiality, but a situation of plane strain in which you don't have necking.
Okay.
So the triaxiality plays a role in reducing the yielded region at the root of the notch. The smaller the root radius, the smaller is the region where triaxiality causes general plastic deformation at the notch. And so, since that region is less and less as you reduce the radius, also the region of the controlled by the slip bands is smaller and smaller, and the amount of energy that is consumed in the structure process decreases.
Okay. It's very clear. Thank you so much for the answer and for the clear explanation. I ask again if there is a question from the audience. Otherwise, we have finished almost the time, so we can go to the next speaker. Thank you again to Professor for the excellent presentation. Outstanding, I would say.
Thank you very much.
Yeah, so now we have another very important speech that came from Andreas Brunner with Bamber Blackham and Lauren Warnett. This talk is also linked to the ESIS TC4, where they are doing a great work together to contribute to the European Society of Structural Integrity. So it is a great pleasure to introduce these second lectures, and the title is Years of Standardization and Research on Fracture of Polymers, Polymer Composites and Adhesives in ESIS TC4, Past Achievement and Future Directions. I'm very happy to welcome Andreas, Professor Andreas, for this presentation. Thank you so much.
Okay, hello everybody. Can you hear me?
Yes.
Okay, I'm trying to upload my presentation, but somehow the screen doesn't allow me to do that.
Yeah, if you have the button where it is written share screen.
Yes, but then I get a window that asks me to allow access, and even if I do it, it seems it doesn't help.
But actually, we are seeing your screen, but
you can see it. Okay.
Yeah, but the presentation is not visible.
You see the PowerPoint?
No, not the PowerPoint. We see the desktop.
Okay. So just as a brief summary, the main aim of the presentation is to kind of advertise the activities of ESIS TC4, as you mentioned in the introduction. And this is why I'm focusing on future activities and not the past achievements. So one area is fiber-reinforced composites and fracture of these. So far, these materials become widely used in many industrial sectors, but there are no standards on cyclic fatigue fracture testing available yet. And in one photograph, you see a part that failed due to cyclic fatigue loads. And there is also an issue with fiber bridging. And so the questions here are, what is the role of fiber bridging and how can safe design limits for these materials be determined from experiments? A second question is, can simulation reduce the design and experimental validation effort, which for some structures, for example, in aerospace applications, is quite significant. Another open issue is how do environmental effects change the fracture behavior of polymers and composites? This is just in the beginning, and we're starting a round-robin activity on that. And a final, also quite interesting area is the question of new digital tools. Can they be implemented in experimental fracture testing, for example, to reduce scatter, or would even full automation of testing and analysis be feasible? And as a final remark, anyone interested in this kind of activity is welcome to contact us, and all the details can be found on this website here. Okay, so that concludes my short summary of the presentation, and I'm open for questions now.
Thank you so much. So I would like to ask if there are questions from the audience, they are welcome. I hope that there is a question from the audience. Okay, if there are no questions from the audience, I want to thank you for the great activity that you are doing inside TC4. And actually, I would like to ask you, you mentioned now about digital tools that can be implemented to create a better organization of the standards and probably of the data that we can have from different communities. So I would like to ask which trends do you think are the best in this direction, and which is the future developments that you consider important in this field?
Okay. So digital tools can be used in several areas or aspects of the standards. One that I think will become very important is where digital tools help reduce scatter due to, let's say, human effects like operators visually trying to follow a crack or delamination propagation, which of course is a rather subjective thing. And people nowadays are using more and more digital recording, either still images with digital cameras or full video recording. And that can then be combined with image analysis, again, a digital tool, to get more accurate and more consistent delamination length values for the further analysis, for example. So this is, I think, where the benefits are most obvious. To illustrate it, typical scatter in round-robin data, for example, for polymer matrix composites, are on the order of 10 to 20%. And it is likely that most of that comes from kind of operator-dependent effects like this visual observation that is the current standard form of determining delamination length. However, there are other aspects where digital tools can be useful, for example, in data analysis. If it's, let's say, a large amount of data, it is much easier to use respective tools. Could be anything that can handle these amounts of data to, again, ensure consistent evaluation of the data that then will give comparable data where the major source of scatter is then the material variability. And this is what you want to catch really in the tests. This material variability, of course, comes from the manufacturing and processing, and possibly also from environmental effects. So it is important to know how much scatter is introduced by that, because if you base structural design on these data, these effects have to be taken into account. So this is another example. I mentioned full test automation. Of course, that again will be a question of the suitable digital tools. So you have to have a test machine control, maybe a robot putting in specimens, taking them out. And that, of course, may not change the scatter much, but it will be, or it could be, an important cost factor. So you could save on human operator cost, and robots will work 24 hours, 7 days a week if you want them to, unlike humans who obviously want to go home in the evening and have their weekends off for leisure. So these are examples where I see probably the most immediate benefits of digital tools. There could be in the future further aspects like analyzing large amounts of data, maybe with kind of support by artificial intelligence to make to identify potential differences that still persist in the data, and really get more uniform and in that sense more useful data.
So I think, thank you very much for your explanation, and congratulations for the work that you are doing for TC4. Thank you so much. Now I think we can go ahead with the next presenter. If Andreas, you can remove the share of the screen. Yes, perfect. So the next speaker belongs to the group from Julio Ruiz, Vilches, Gonzalo, Dominguez Almaraz, Mario Sanchez Medina. And the title of the work is Managing 300 Steel Under Ultrasonic Fatigue Tests at Room Temperature. So I invite the speaker of this presentation to briefly introduce his work, if he is present. Is any of the author of the paper Managing 300 Steel Under Ultrasonic Fatigue Test at Room Temperature present here? Okay, so I think we can go to the next speaker and we can wait for him later. So the next speaker will be fatigue resistant notch structures enabled by artificial intelligence. And the group of work is Xinbo Wang, Chao Gao, and myself. So I would like to ask Xinbo to introduce his work. Is Xinbo here? Okay, so we have also this paper not present. So I think, is any of the authors of this section here?
Filippo, he's there. He's there, but he's muted, I think.
Xinbo, you have to unmute yourself. So you can share your screen and make a brief introduction of your work. Xinbo. Perfect, but we cannot hear you. We cannot hear you. We have seen the video. We have seen the screen, the sharing of the screen, but we didn't hear you. You can start. We cannot hear you. Xinbo, you have to unmute yourself. We cannot hear you. You can use the microphone of the computer or change room. You have the microphone that is not working. We cannot hear. We cannot hear you. You have to activate your microphone. Or ask to a colleague to borrow the computer and make the presentation there. Or simply connect with a mobile and without slides, you can say a few words of your work. So probably you can solve your internet connection problem and the microphone problem, and we will come to back you later, okay? So you can be the last. So I want to ask if Danilo Renzo, one among Danilo Renzo, Carmine Maletta, Emanuele Sgambiterra, or Franco Furgiuele are here.
Yes, good morning.
Yes, good morning. So I think you can go ahead with your work, which is entitled Surface Roughness Effect on Multi-Axial Fatigue Behavior of Additively Manufacturing Titanium Alloys.
I share my presentation.
Yeah, perfect. Yeah, fantastic. It's working.
I can start.
Yes.
Okay. Good morning. I'm Daniel Lorenzo from University of Calabria, and the title of this present work is Surface Roughness Effect of Multi-Axial Fatigue Behavior of Additive Manufactured Titanium 6 Aluminium for Vanadium Alloy. The aim of present work is the analysis of fatigue behavior of additive manufactured titanium under proportional axial torsional loading using two different batches of sample with different surface conditions as built and machined. Before each test, the surface roughness was measured for each test, for each in-wall tubular specimen, in order to analyze the effect of surface roughness. Maximal deep parameter is considered as the worst surface condition because, as shown in several studies, it can be considered as a micro notch, where the stress concentration factor acts at the deepest point of valley, and that leads to crack initiation and produce a decrement of fatigue performance. In this slide is a comparison of fatigue cycle properties is reported, and we can conclude that surface roughness have have a detrimental effect on fatigue performance. In fact, the fatigue strength decreases with the increase of surface roughness. In addition, a parameter considering the synergic effect of roughness with the multi-axial state of stress, a parameter based on an effective strain density factor that incorporates the maximum valley deep parameter, is defined and is used for the correlation of fatigue data. And the use of these parameters seem provide a better correlation of fatigue result with respect to the equivalent stress amplitude, as shown in the graphs. Tool feeds techniques as digital image correlation and infrared demographic analysis are used to evaluate the accumulation of effective mean strain and the temperature evolution on the gauge ledge of sample. And the major accumulation of effective mean strain was observed for the as-built sample with respect to machine sample at the same level of the stress. And demographic analysis show an higher level of final temperature occurs for an higher level of stress for both type of the sample. In conclusion, the polar plot of normal and the shear stress superimposed to factor image of sample of both type of surface condition was used for the analysis of critical plane orientation. The figures show that for both type of the sample, the factor surface, the factor plane have an angle near to the plane, the orientation plane where acts the maximal mass stress, and for both type of surface condition. And this suggests the failure occurs under tensile loading. Thank you for attention.
So thanks a lot, Danilo, for the presentation. Is anyone from the audience that has questions? Please don't be shy. And if you have questions, you can make it. So I have a curiosity. I'm also author of this work, but I want to understand your idea about this. So as a future development of the work, which is your plan and which is the idea of developing the method for example, for other geometries or for other more complex structures?
Yes, in particular, I have an idea on to modify the factor, the parameter based on the factor mechanism model, and I would modify these terms, introducing the idea of Murakami, that consider the area of crack. And I would also modify this model to consider for apply for element with a higher thickness, and consider not only mode 1 and mode 2 of loading, but also the mode 3 of loading. And
I think the plan is very good. So I would like to thank you for the presentation. I ask again if there are questions from the audience. Otherwise, I will try with the next speaker. Is any question? Okay, so I want to thank you, Danilo, for the nice presentation and for also replying very well to the question. And now I think we can go back to the speaker that was missing before. And in particular, can you unshare, Danilo, the screen? Yes. So the next speaker are the authors of Meraging 300 Still Under Ultrasonic Fatigue Tests at Room Temperature. The authors are Giulio Ruiz, Vilcens, Gonzalo, Dominguez Almaraz, Mario Sanchez Medina. Is any of these author present? Okay, so no authors of this paper is present. Shimbo, are you able to speak now? Shimbo, we cannot hear you. So I think we can go to the speech of Pedro Costa, Luis Reis, and Manuel Freitas, that is with the title Ultrasonic Fatigue Testing Under Biaxial Stress States. I see that Luis is present and is able to speak. So I like to introduce and to thank you, Luis, for the nice presentation that you will do for us.
Okay, hi Filippo, can you hear me?
Yes, hi. Perfect.
Oh, okay, good. Well, thanks for the presentation. I'm Luis Reis, professor at the Institute Superior Técnico in Lisbon, Portugal. Well, it is a great pleasure to be here and to participate in this conference. I'm going to share my presentation. So we have here 2 or 3 slides. Let me see. Okay. So I think now you, okay. Okay. Oh,
yes, it's perfect.
Good. Okay. So, well, just 2 or 3 slides. Here are the main objectives of this work. So we are in the last periods of time, we are doing some tests and characterizing and evaluating materials under multi-axial fatigue. So at very high cycle regime. So it means we are talking about 10 power 7, 10 power 9 cycles. Another objective is to evaluate different torsion tension ratios. So we are now proceeding with this kind of research. So, well, how to achieve that? We are using an ultrasonic fatigue testing machine. In this case, we are considering 20 kilohertz. So it means that, as you can see here on the right side on the picture, that the set of the booster, the horn, and the specimen should be tuning in order to resonate at 20 kilohertz. Well, other challenges appear here. Well, it means that the horn and the specimen should be designed in order to induce torsion in the specimen. Another issue is that we should define a specific region for to measure the stresses that we are evaluating. So these are, let's say, the main issues that we should deal with. So we have been designed several geometries for the specimens. I just put here 2 of them with different torsion tension ratios. In this case, 0.5 and 0.38. So as you can see, we have different geometries, different diameters, lengths. So which means that we have also different masses and so on. Of course, we have also to perform finite element analysis because we need to tune all the set, as I said before. So here we have the first longitudinal resonance mode, the axial one and the rotational one. And here, oops. And here we have the combination of the two modes here. Okay, so here in the right side, we have the fracture surface of the specimen. This is just an example. And the material is the P20 steel, is a high strength steel. And well, as the main conclusions of this work, I could say that well, tension torsion fatigue tests were carried out with the specimens geometries with different torsion tension ratios. Crack initiation angle is depending on the stress ratio and also of the stress intensity. And also that higher stress ratio specimens show more pronounced torsion fatigue marks. Okay, so I'll conclude. Thank you very much for your attention.
Thank you a lot, Luis, for the nice talk and nice presentation, and also for putting light on this interesting topic. We have some experts here about the topic. I see in the list of people Andrea Tridello and also Davide Paulino. Is any question from the audience, especially from the experts on the topic?
Thank you. Yeah, thank you, Filippo. I have a curiosity, a comment, and I would like to say, first of all, that I appreciated a lot the work, and indeed it's something that we would like to carry on also in Politecnico, something related to multi-axial very high cycle fatigue. And just to start also in Politecnico, I would like to ask you if you have any method to check the actual stress state inside the specimen during the test, since it's quite complicated according to the finite element models. Yeah, of
yes.
course, something
everything
occurs.
Seems perfect.
Yeah, but
yeah, sure.
As you know, since you are an expert of this kind of test, it's quite complicated to be sure of what happens during the test.
Yes, it's true. And sometimes we are talking about microns, so we need to be very careful with the geometry of the specimen. But I can show here, I have here more slides. Let me show just to answer your questions. Well, this is we control the temperature, but I want to show you. Oh, Pedro is talking, but we have. We have calibrated the specimen, which means we have, I think, well, I don't have here, but we have glue some rosettes, some strain gauges in the throat of the specimens, and then we have to pick these two graphs here were achieved for each specimen. And as you can see here, we have a linear curve for both, for the axial and for the shear stress. But we need to measure locally. We have to glue a very teeny, very small strain gauge in the throat, in the main throat, where we are interested, of course, to pick the values. And as you can see here, we experimentally, as you mentioned, we need to validate and to compare with the results from the finite element analysis. It's very important.
Thank you very much. I totally agree that a validation is something that it's important, relevant.
Yeah.
Thank you.
Because here the things happen very, very fast.
Yeah, yeah. we have to be confident.
Yeah, sure.
In some way.
Thank you very much, both for the presentation and also for the nice discussion on the topic. Okay. And so I think we can go ahead with the next speaker.
Okay, see you.
Luis, you can unshare the screen. We can see if Shimbo is able to speak.
Shimbo? Could you hear me now?
Yes, yes.
I'm
Now
so
you
sorry.
can hear you.
Yeah.
No, it's fine. No, it's not a problem. You can share your screen.
Okay.
So, yes.
Yeah.
So now everything is working, and so
Yes.
you
Okay.
3 minutes.
Yeah.
3 minutes. How much you want to present? We are
okay.
flexible.
Okay. So. So inspired by the sunflower joint, we want to use a data-driven approach to design a fatigue-resistant node structure under the different loading conditions and through numeric simulations and deep learning. So along these arrows, this is research direction. Here I just made a summary about the whole of the presentation results. And first, we generated so many different geometries according to a strategy we called the gradient descent strategy, and used this B-spline line to avoid the stress concentration singularity. Here we inspired from this sunflower joint geometry, we generated this kind of different geometry shapes just in this actually you can hear this is just from this space, the range is 12 by 12 space. So since in this project we used the deep learning method is the convolutional neural network model, and the convolutional neural network model is very suitable for analyzing the image data. So I translated the geometry to image first, and then we input this image after the visualization and the corresponding straight energy density volume after the finite element analysis simulations into this convolutional neural network model. And after different layers training, it can give a prediction for the target object. And after this prediction, we can output some fatigue-less design. And since from the prediction, from this convolutional neural network prediction, the target SLED value is related to the corresponding geometry, and this geometry they'll have a regular of their distribution, and from this distribution we can also see some regular of the geometry design, and from this distribution we also can select some geometry which has a high fatigue resistance. Okay, that's summary of my research project.
Yeah.
Thank you for your attention.
Thank you very much. Is there any question from the audience?
I have one question.
Yes,
okay.
Perfect.
Thank you for your nice work. This approach, the result that you obtain is similar to that can be obtained through shape optimization, for example. Do you compare the results that you obtain through this approach with shape optimization, or is this approach more efficient than traditional optimization? It is just a curiosity.
Yes, actually, we can't say it's optimization because the convolutional neural network is optimization method. In this project, we just want to use this convolutional neural network model to help us to build a method to design this kind of fatigue-resistant node structure design. I mean this process, not to find the optimal one, but from the prediction results, yes, we can maybe yes, we can find some cases that have a high fatigue resistance, especially according their strain density value. We can see if the geometry's SAD value is lower, which means it has a high fatigue life, which means we can say it's a fatigueless design. And after the prediction, we also have a comparison with some standard notches here, especially this constant notch, which means it generated a quarter of, I mean, the radius is constant. And we also compared with the sharp V notch, blunt V notch with our predicted fatigueless notch. And we can see from the predicted strain density value, we can see here, you see, the convolutional neural network model shows some benefits with some what we use the normal method, and it also shows some benefits with some standard notches.
Okay, thank you. And how long does it take you to obtain the result?
You say what kind of results?
To obtain the optimized, the final result.
Which is the time, the computational time?
Yes.
Computation time. Okay. Computation, yes.
Not the one that you obtain, about.
Approximately.
Sorry, could you say again about your question? I'm a little confused.
We mean, which is the computational time that you need for obtaining optimized geometry according to your model? Actually, your model. How many days, hours?
Okay. It's very fast. Yes. It's
okay.
Yes, it's very fast. I think the time more cost on here, maybe just for preparing the data set here for yes here for simulations. So many. I mean, at first we need a data set for have a preparation of our convolutional neural network model. I mean, we need to generate a data set for training. And here we, after so many different training, we think at least we need almost 10,000 cases for this training data set. And I think the most time was cost in this place. But about the you said the optimization process, but for me it's the prediction process. Actually, this process is it's very fast.
Okay, thank you very much for your explanation.
Thank you.
And thank you, Andrea, for the nice questions and for the useful discussion that you make.
Okay, so thank you, Filippo.
I think, Shimbo, you can unshare your screen.
Okay.
And now we can try again with the second presentation of this section, that was Meraging 300 still under ultrasonic fatigue test at room temperature, with authors Julio Ruiz, Vilches Gonzalez, Dominguez Almaraz, Mario Sanchez Medina is one of the authors here. If not, we can go to the last presentation, which is with the title Nonlinear Numerical Study of Stainless Steel Profile for Fatigue Experiment. The authors are Lukas Bright, Peter Miarka, and Stanislav Seitel. Is any of these authors here? So I think we miss two presentations and two speakers. I also know that we have a speech that remains from yesterday, so we can try to have this speech now. Is Malgasheva Irina present to the present online?
Yes, yes.
Yeah, perfect.
Good
So,
day. Good morning.
Yeah, good morning. You can go ahead with your presentation instead.
Yes, yes, of course.
Thank you so much.
Thank you.
You can share your screen if you want, or simply speak about your work.
Okay. Good day, ladies and gentlemen. Thank you to the organizing committee for the opportunity to make my presentation at this conference. I am presenting a report scaling laws in fragmentation, dynamic of rock materials.
Irina,
Ow.
Do you want to share your screen or simply speak?
Так, okay.
It's up to you.
Yes.
As you prefer. I mean.
Are you screen?
Yeah, now it's visible.
Yes.
You can go ahead with it. Yeah, we see the presentation now.
Okay. I am star.
Yeah, go ahead.
My work was carried out at the Institute of Continuous Media Mechanics, oral branch of the Russian Academy of Science in the Laboratory of Physics, Foundation of Strength. The work was carried out with the financial support of the Russian Foundation for Basic Research. In our work, an actional compression tested for rock quad-side cylinders were carried out quasi-statically and dynamically. The destruction process was accompanied by fractoluminescence. The glow was recorded in two ways, with a photomultiplier and a high-speed camera, which was able to record the destruction process itself. A statistical analysis of the fragments mass distribution is carried out. The distribution is described by two Paul laws, foliage, and small fragments with an inflection point. This behavior corresponds to brittle fracture. The aim of this work to experimentally study the fragmentation of the rock materials from considered quartz based on the study of the laws of fragment size distribution or fragments mass distribution under conditions of quasi-static and of dynamic compression. With joint registration of fractoluminescences that will be contribute to the establishment of a relationship between the self-similar laws of deformation and of structure with multiscale mechanism of the structural relaxation caused by the behavior microscopic defects. That's all. Thank you for your attention.
Thank you a lot, Irina, for the nice presentation and for the nice topic, a bit different from the rest in this section and original. Can someone from the audience make a question? Is there any question? If there is no question, I have a curiosity. Which is have you tried to make a tomography of your samples, or have you planned to understand which is the kind of defect size that you have inside your sample before the testing? Or have you planned something regarding to this, or some techniques to actually see the condition of the samples before the test?
We for example,
Okay, nice.
On a sample of number 4, we used high-speed camera. The slide showed frame for the video recording of fractal elements in the destruction process. The video camera recorded signal flashed correspond to the initial of micro damage in the sample. One signals zeros one time prolonging luminance prolonged corresponded to macro cracks, and subsequent signal flashed correspond to the destruction of fragments.
Yes.
The results are comparable to the signals from the photomultiplier. Signal impulses, and multiplier impulses. 1A, stage 1 of destruction in the spirit of fracs from stress concentration, and stage 2 of destruction in the complete destruction of the sample.
Yeah, thank you so much. It's clear. So thank you for your explanation, and I think we can move to the next speaker if it is present. So thank you, Irina, for the nice presentation. If you can unshare your screen, we can go to the next speaker.
Thank you very much.
Thank you, Irina.
Goodbye.
So the next speaker is again, we try to call the persons that are authors of the paper Managing 300 steel under ultrasonic fatigue test at room temperature. The authors are Julio Ruiz Vilches, Gonzalo Dominguez Almanaz, Mario Sanchez Medina. If there is no one of the speaker, I think this is the last call. And I also call for the last time the last paper that is from Lucas Bright, Peter Miarka, and Stanislav Seitel, nonlinear numerical study of stainless steel profile for fatigue equipment. Is someone of these author present? So I think in this case, we can conclude this first section, and we can leave the people to go to the coffee break and to have a rest before the next section. So I want to thank all the authors and all the audience that has attended this section, and we will wait you for the next one. So thank you so much. I will conclude now the section, this section, and you can take a coffee also remotely.
Okay,
Bye.
Philippe. Thank you.
Thank you. Thank you.
Bye.
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 по-добре нещо да не ни навали дъжд, докато чакаме там таксито. Това е малко... Добре, айде, 9:30, пък се надявам, че... Айде, 9:30.
Good morning. Luciana, sei online? Luciana?
Eccomi, buongiorno.
Ciao. Buongiorno.
Ciao, buongiorno a tutti. Good morning. We have 3 minutes or we can start?
3 minutes.
Okay. Okay, we start at 11. Good morning, everyone.
Good morning.
Good morning. I'm Luciana Restuccia from Polytechnic of Turin. And as chair lady, I welcome you to this session, that is number 10. The presentation of this session are in total 9. And I believe that they will be very interesting due to the heterogeneity of the topics. The authors of the first speech are Professor Thea Maronic and Professor Robert Bazin, and the work is entitled The Estimation of Materials Parameters of Strain Life Fatigue Behavior using Empirical and Artificial Neural Networks-Based Approach. I'd like to ask to the speaker, that I think is Professor Thea Maronic, to share her presentation and start the discussion.
Thank you for the introduction. I will share my screen. Can you just confirm that you see it?
Yeah.
Yeah, okay, thank you. So I will try to be brief. So you heard about our topic, and I suppose some of you are familiar with empirical methods for estimation of fatigue parameters from strain life behavior expression, Baskin-Coffin medicine. However, these empirical methods have some drawbacks, which we established, so they don't take into account different material groups. They are sometimes developed on quite small data sets. Certain parameters are assigned constant values, which is particularly problematic if we consider all materials in together, and there is no prior statistical analysis for identification of relevant monotonic properties for their estimation. So we developed a new approach. Based on prior statistical analysis, we established relevant monotonic properties for estimation of each strain life parameter. We developed artificial neural networks for estimation of each parameter, and then we used that to estimate strain life curves. So to establish the performance of these artificial neural networks, we used independent set of data, which was not used for their development. And we compared estimations to experimental values for parameters and for behavior, and compared their performance to well-known empirical methods. I won't go into details for each diagram because we lack of time, but dark blue is performance of artificial neural networks for each parameter. We considered unalloyed steels, low alloyed steels, and high alloyed steels as separate groups. And we can see that performance of AN and Ns is quite good. So for each parameter, especially these exponents, if we check, we see that for B and C, there is usually a constant value assigned. So parameters are one thing, but when we estimate behavior, we obtained such diagram, and we could see, so this is evaluation performed for 6 data sets of 4140 low alloy steel. And we can see that artificial neural networks are somewhat better. It depends on the scatter band. But we then randomly chose one data set to see what happens when we draw curves. And here is a diagram showing artificial neural networks estimated curve compared to experimental, and curves that are estimated with those conventional methods. And we can see that artificial neural networks predict these curves quite good. We can say qualitatively quite better than these other methods. So in conclusion, we can say that artificial neural networks can be a promising tool when developed correctly, of course, for estimation of material strain life parameters and behavior. We are currently dealing only with metallic materials, specifically steels, and we have some planned research activities also to do in future. But I will stop now because I think I don't have time left.
Thank you. Thank you very much for your interesting presentation. Are there any questions from the audience? I think no. I have not a question, but a curiosity, because the topic for me is novel. Could you explain us briefly how you developed the neural network architecture in order to carry out the prediction of materials parameters?
Yes, can I just share a slide from the full presentation? So that's written. Okay, I won't spend time on that. So when developing artificial neural networks, it is quite important to determine the proper number of neurons in hidden layer. So we use growth methods. We actually developed methods that contained one neuron in hidden layer, and we from 1 to some upper level that is determined by the number of data used. So you, when developing networks, you have to ensure that the network parameters that have to be fitted, let's say, don't be higher than the available data. So we limited that complexity according to a certain expression, and we checked performances of these networks for each architecture, and checked what happens. Also, since the number of data sets available is quite small when talking from perspective of artificial neural networks, but it is quite high when considering fatigue tests. We used k-fold cross-validation to train networks, so we can use that data in the best way possible, so the networks can learn as much as possible. I hope I
okay, thank you. And I saw that there is a question in the chat. Jamal asked what consideration you recommend if you want to use artificial neural networks for, say, polymer composites?
I am not comfortable to answer that question because I do not deal with polymer composites, and I suppose you have to establish also some the relevant parameters, and then try to maybe use something similar, statistical analysis of something to determine that and start from that. So as far as artificial neural networks are considered, there are quite a lot of possibilities. We used multi-layer perceptrons with backward propagation that are said to successfully approximate most of the functional approximation. So yeah.
Okay, thank you very much, Thea, for your presentation and for answer to the question. I think we can skip to the second speech. The title of the second speech is Effects of Strain Recovery on Longitudinal Fracturing Continuously Inhomogeneous Viscoelastic Beams. I will ask to Professor Rizov to share his screen, his presentation, and start the discussion.
Thank you. Now I'm going to share my screen, but what? Can you see the screen?
No, for the moment we see only the...
Okay. I clicked on share the screen, so...
maybe you click on Firefox HTML, not the presentation in PPT.
This is actually the file that I want to present. This is a PDF file, but why it doesn't appear on your screen? And here there is a message that your screen sharing is paused, but why?
Try to close and reopen and reshare.
Okay.
Thank you.
gain 2.
Okay, now it works.
Yes, thank you.
Thank you.
This paper actually studies the influence of strain recovery upon unloading on longitudinal fracture of a continuously inhomogeneous viscoelastic beam. The creep behavior of the beam is treated by using a linear viscoelastic model. The modulus of elasticity and the coefficient of viscosity of the model are distributed continuously along the thickness and the length of the beam. A longitudinal crack is located symmetrically with respect to the midspan of the beam. The time-dependent longitudinal fracture of the beam is analyzed in terms of the strain energy release rate. For this purpose, time-dependent solutions of the strain energy release rate are derived by using the strain energy accumulated in the viscoelastic beam. Time-dependent solutions of the strain energy release rate are obtained also by considering the beam compliance for verification. The solutions derived are then applied to study the variation of the strain energy release rate with time. The study reveals that the strain energy release rate increases with time. This behavior is due to the creep. Upon partial unloading of the beam, the strain energy release rate decreases, and this finding is attributed to the instantaneous recovery of part of the strain in the spring of the model. A parametric investigation of the time-dependent longitudinal fracture is carried out. First, the effect of the length and crack location along the beam thickness are investigated. It is found that the strain energy release rate increases with increasing of A to L ratio. Actually, this ratio characterizes the crack length. The increase of H1 to H ratio leads to decrease of the strain energy release rate. The H1 to H ratio characterizes the location of the crack along the beam thickness. The effects of material inhomogeneity on the longitudinal fracture are also investigated. For this purpose, calculations of the strain energy release rate are carried out at various values of material properties. Actually, these properties characterize the material inhomogeneity in the thickness and length directions of the beam. On figure 2, the viscoelastic model is shown that is used in this study. Figure 3 shows the strain energy release rate in non-dimensional form, plotted against the non-dimensional time. As we can see, the strain energy release rate decreases with time, which is due to the creep. And when the beam is unloaded partially, we have this drop in the curve, and then again, the strain energy release rate again increases with time. Figure 4 shows the strain energy release rate in non-dimensional form plotted against beta. Three curves are shown for three volumes of A to L ratio. We can see that the strain energy release rate decreases with increasing of beta. And also the increase of A to L ratio leads to increase of the strain energy release rate. Figure 5 shows the strain energy release rate plotted against the parameter beta F. Three curves are shown for three volumes of the H1 to H ratio. We can see that again the strain energy release rate decreases with increasing of beta F. Also, the increase of H1 to H ratio leads to the decrease of the strain energy release rate. The strain energy release rate is shown in this figure, plotted against the parameter delta. Again, three curves are shown for three values of the parameter delta F. Here we can see again that the strain energy release rate decreases with increasing of these parameters. The strain energy release rate is shown in this figure, plotted against the parameter rho at three values of the parameter rho F. And we can see that the strain energy release rate decreases with increasing of rho and with increasing of rho F. Actually, this is my short presentation. Thank you for your attention.
Thank you, Professor Ries.
You are welcome.
Are there any questions from the audience?
Yeah, Luciana.
Yes, I have one. Okay, excuse me.
Okay.
Yeah.
Yes.
Giuseppe, please.
After you, please.
Thank you. I have one question for the first slide. This is very interesting situation.
First slide,
First
where
slide.
the beam is shown.
Yes, this beam.
Okay, this is the beam.
This is.
Yeah.
It's very interesting for me that notch is in the vertical plane, or vertical direction, and crack is in the horizontal direction.
Yeah.
I see that this is relatively short length of this specimen, of this body, and that high influence can be from shear stresses. It's this effect. Why this crack propagate in the horizontal direction? High influence of shear stresses.
Yes.
Relatively short beam. Yes.
The problem is that this picture, figure 1, is not in scale. I mean that the aspect ratio of the beam is quite high. I mean the ratio of length to thickness of the beam is high. So here it is, again, I have to say, it is plotted not in scale. So it's a bit not very correct presentation of this beam. In other words, here we analyze the long beam. Actually, in the portion between the two supports, the beam is in pure bending. So we don't have here shear force and shear stress. Certainly, and because of the beam is quite long, with high aspect ratio, we don't consider this effect of shear stresses in this case.
Okay, thank you.
I think there is another question from Professor Ferro.
Vladimir said noticed the same problem, because in poor shear it's very difficult to obtain this kind of crack, at least if it is present before the test. It's like the lamination, and in this case the lamination is very difficult to occur because shear is zero in this area. Okay, that's all.
Okay, thank you. And in reality, I asked to Professor Rizov to share again the presentation because the third speech of this session is always by Professor Rizov. The title of this second work presented by Professor Rizov is Lengthwise Fracture of Functionally Graded Beams, a study of stress relaxation effects.
Thank you. Now I will share the screen. Okay. Can you see my screen? Not?
No, for the moment we have the same problem of the previous presentation. We are not able to see your screen.
The same solution, close and open again.
Yeah.
I think that now it
Okay, now it works.
Yes. The influence of the stress relaxation on the strain energy release rate for a lengthwise crack in a functionally graded cantilever beam configuration is analyzed in this paper. The stress relaxation is treated by using a linear viscoelastic model consisting of a spring and a dashpot. The modulus of elasticity and the coefficient of viscosity are distributed continuously along the thickness of the beam. A time-dependent solution of the strain energy release rate that accounts for the stress relaxation is derived. For this purpose, the balance of the energy is considered. A time-dependent solution of the strain energy release rate is obtained also by applying the compliance method for verification. The solution of the strain energy release rate is used to investigate the evolution of the strain energy release rate with time. The analysis reveals that the strain energy release rate decreases with time. This behavior is due to the stress relaxation. The influence of the crack location along the thickness of the beam on the strain energy release rate is also evaluated. It is found that the strain energy release rate decreases with increasing of H1 to H ratio. This ratio characterizes the crack location along the thickness of the beam. The influence of the material gradient on the strain energy release rate is also studied. The calculations indicate that the strain energy release rate increases with increasing of ELW to U to EU P and eta LW to eta U P ratios. A time-dependent solution of the strain energy release rate is derived also for the case of material with different viscoelastic behavior in tension and compression. The investigation shows that the strain energy release rate for the material with different viscoelastic behavior in tension and compression is higher than that for material with identical viscoelastic behavior in tension and compression. The analysis developed in this paper can be applied in design of functionally graded members and components which are subjected to stress relaxation. The beam under consideration is shown in figure 1. The model, the linear viscoelastic model that is used, is shown in figure 2. This is the cross-section of the lower crack arm. Figure 4 shows the strain energy release rate plotted against the non-dimensional time for 3H1 to H ratios. Here we can see that the strain energy release rate decreases with time. And also the strain energy release rate decreases with increasing of H1 to H ratio. This ratio actually indicates the position of the crack along the thickness of the beam. Figure 5 shows the strain energy release rate plotted against ELW to EUP ratio. Three curves are shown for 3 eta LW to eta UP ratios. We can see here that the strain energy release rate increases with increasing of these ratios. Figure 6 shows the strain energy release rate plotted against the non-dimensional time for the case of material with different behavior in tension and compression, viscoelastic behavior. We can see that the strain energy release rate decreases with time and increases with increasing of eta CLW to eta CUP ratio. Figure 7 shows the strain energy release rate plotted against ECLW to ECUP ratio. Again, here we can see that the strain energy release rate decreases with increasing of these ratios. The strain energy release rate here is plotted against UF. This is the longitudinal displacement. Two curves are shown for material with identical viscoelastic behavior in tension and compression, and for material with different behavior. We can see that the material with different behavior, for this case, the strain energy release rate is higher. Thank you for your attention.
Thank you, Professor Rizov. Are there any questions from the audience?
Yeah, Luciana, may I ask Professor Rizov, sorry, from the first figure, I suppose that the boundary conditions, so the analysis is conducted in displacement. So you fix the displacement in the free end of the beam. Again, very difficult.
Yes, that's correct. We
understand how the crack, because the upper part of the crack is completely free of stress.
Yes.
So
the upper crack arm is free of stress.
Completely free of stress. So I can catch the. Also in this case, we have not shear. It's look like some delamination. So the crack it's present before the analysis.
Yes.
I can understand how crack influence the solution in this case.
Actually, this model, being with a longitudinal crack loaded in this way, I have found similar solutions in the literature, but for a linear elastic material without considering any time-dependent behavior. So this situation with this loading and so on has been analyzed by other authors by using the same model, the classical beam, long beam, and by considering only the normal stresses which are induced by this displacement UF. Here, actually, I have expanded this solution for the case when the beam has linear viscoelastic behavior. So this time-dependent behavior.
What is the stress distribution in linear elastic analysis of this kind of geometry?
Sorry, I cannot.
In your opinion, what is the distribution, the trend of the stress inside the specimen in linear elastic analysis?
Linear elastic analysis, the stresses are distributed non-linearly actually because the material is inhomogeneous, to say functionally graded material along the thickness of the beam, and therefore the stress distribution is non-linear due to the material inhomogeneity along the thickness of the beam. And again, I have to say that here we consider only the normal stresses.
Because there are only normal stress.
Yes.
That's why it's difficult to understand the position of the crack. However, my problem. Thank you.
Yes,
you are welcome.
Giuseppe, I mean, excuse me, Giuseppe, I mean that this is the influence of shear stresses between the layers, because this is the different Young modulus between layers, and different same elongation create different stresses, and between the layers induce shear stresses.
Is it the bonding?
Yes, this is the delamination, but delamination is the shear.
Yes, the bonding.
Okay, thank you very much for your intervention. And we can go to the next speech. I kindly ask to Dr. Beibei Xiong to share her screen and start the presentation. The work is entitled The Experimental Characterization of Mortar with Recycled PEIT Aggregate Preliminary Results. So when you want to start, please feel free to do.
Hello everyone, I'm Beibei from the Polytechnical di Torino, and today I will show some results about the recycled PET aggregate in mortar. Okay, from all the figure you can find the plastic is very easy to see in our daily life, and they have many types of them, PET, PVC or PE plastic. And you can find in the package of this plastic, and they will give the recycling code of them. And here we will give the common density range of different type of plastic. Yes, let's go ahead. And normally we will think the shape and the size of plastic aggregate have great influence of the characteristics of mortar or concrete. In our study, we will use the PET powder, and here this figure will show the particle size of this type of aggregate. And this is the basic mixed design of a plastic substitute in mortar and concrete. Okay. And in our study, we will apply this type of the proportion. We will substitute the motor by volume, and the volume substitution level is from 5 to 30 here. And this figure is showed the specimen for the flex rotates. And here we will have the notch in the middle of the specimen, and the width is 5 millimeter, and the depth is 12 millimeter. And this figure will show the mean result from the load and deformation curves from the tape on 7 days. And here is the strength from the tests. And here is the compressive strength. Yes, because all the tests are based on the 7 days. So here we just show some of the result on 7 days. Okay, it's finished.
Thank you, Bei, for your presentation. Are there any questions from the audience? Maybe no. I'd like to ask if you can summarize the influence of using a PIT in the realization of mortar mixture. I mean, you see a strengthening of composites, you obtain flexural strength and compressive strength that are comparable to the reference one?
Yes, maybe from this figure is easy to check, and we can see from this figure that the with PET aggregate we will decrease the strength, but from this figure we can see it will enhance the ductility of the motor, which means with the higher substitution level of plastic, and we will have the better ductility of a motor. Yes.
Okay, and in your opinion, what is the economic influence?
Luciana, sorry, speaking.
Yes. Yes, please.
Luciana, may I speak?
Yes.
Okay, thanks. Sorry. So first of all, thanks for the nice presentation, Bei. I was just wondering why you evaluated the strength using notched beams. Okay. And the other question is if you evaluate also the fracture energy, because from your plots seems that fracture energy is increasing, so this can be a very good result for your research purposes. Thanks.
Yes, we applied the notched specimen because we want to evaluate the fracture energy, as you said. And actually, we also have the result showed that the fracture energy will increase with the higher substitution level. Yes.
Okay, thanks.
Thank you, Bei. We can go to the 5th discussion of the morning. The authors are Mirzaei, Sapora, Corrado, and Cornetti. The speech is entitled An Analytical Study on Pure Mode 2 Debonding of Composite to Substrate Joints by Considering the Residual Strength. I like to ask to the speaker to share his presentation and start the discussion.
Hello, everyone. Can you see my screen?
Yes.
Okay. I'm Amir Mohammed Mirzai from Politecnico di Torino. And also, first of all, I would like to thank my supervisors, especially Professor Pietro Cornetti, for his help for this presentation. Okay. I would like to review my presentation, and then I would be happy to answer your questions. The motivation of our work was that for such experiments, load displacement doesn't fall to zero, and it reaches a constant value, which we called it residual strength. So this is the configuration of the problem. We used one-dimensional shear-like model. In order to get the governing equations, we used equilibrium equation, and here is our governing equation, which tau of s should be determined. In this presentation, we used three different constitutive laws to determine tau of s. The first one was Lebbeam, equivalent Lebbeam, and finally coercive crack model. For Lebbeam, the constitutive law for the interface like this, and a schematic view you can see in this picture. Then we move to equivalent Lebbeam. So constitutive law for equivalent Lebbeam is this, and a schematic view would be something like this. And finally, for coercive crack model, the constitutive interface law is this, and schematic view is this. Then we determine maximum load during the debonding for each bond length. We validate our results with experimental. And finally, we define a concept of effective bond length, more detail, and here is the conclusions. The references, and thank you very much. Okay, so I am ready for your questions.
Thank you for your interesting presentation. Are there any questions from the audience? Maybe no. I have a question. What is the difference between lambda lim and lambda effective?
Okay, let me go here. Lambda limit is a parameter that it divides the formulation for long and short bond lengths, and effective bond length is another parameter that here we defined it as beta fraction of the maximum load. If we consider beta equal to 1, both the parameters are equal, but there is a problem here. For equivalent Lebbeam and Lebbeam, we cannot set beta equal to 1 because by increasing the residual strength, the effective bond length decreases and it doesn't have any physical meaning. So we should use beta equal to 0.8 or 80% of the lambda limit.
Okay, thank you.
This is
maybe
the difference between them.
Okay, maybe we have time for another question. So I ask again if are there any curiosity question from the audience? Could you explain us the difference between LEBIM and equivalent LEBIM?
Yes. Okay, I think this is a right figure. As you can see, the model, the interface model for equivalent for Lebbeam is shown by a dashed line, and for equivalent Lebbeam is a solid line. For Lebim, the interface stiffness KT is a known parameter which can be calculated based on the stiffness of the adhesives and the thickness of the substrates. On the other hand, the KF, interface stiffness for equivalent Lebim, is a fictitious number which calculated based on the strength of the interface or tau c. So this one is a fictitious, but that one is a known parameter for the constitutive law.
Okay, thank you again for your presentation.
Thank you very much. Have a nice day.
Thank you. Okay, let's continue with the presentation, and we can move on the speech that is entitled "The Fatigue Strength of Weld Joint of the Gas Pipelines." The authors are Vladimir Chmelko, Pavel Zablek, Thomas Kosko, and Marian Simes. I kindly ask to the presenter to share his presentation and start the discussion.
Can't start. Why?
Maybe because the last presenter have to stop the screening of desktop.
Okay.
Okay.
Okay. Yes. Okay. Do you see my presentation, please?
No, for the moment, no. We are not able to see your desktop.
Excuse me. Okay. Yes, now it's right, yes?
Okay, now it works.
Okay, yes.
Thank you.
Thank you. I'm glad to be able to see you at last in this form, all known faces. And in my presentation, I would like to focus your attention for the 2 points in my presentation, only 2 points. My presentation concerned the assessment of fatigue strength of welds in transit pipeline. This is the gas pipelines. And okay. Yes. First is this slide. First interesting point is this slide. This is the record of pipeline load in the form of maximum stresses in the most loaded cross section, and this record is based of the measurement of using the strain gauges in a special arrangement around the circumference cross section, and this recording latest several years. This is the diagram from 2016, one year. This is the amplitudes from vibration of grounds induced by compressor, and this high amplitude, high peaks. This is the starts and stops of the compressor in this compressor station of this transit courtyard. This is from 2016. Next slide is from 2014. I mean, this is very interesting because this measurement during 3.5 years, and 3.5 years work special monitoring system based on these strain gauges, and we obtain this amplitude and this loading procedure of cross section. And second point, in this measurement was very interesting that we obtain additional bending and this pipes, additional bending. This is the date of this increasing of this bending, and was induced by decreasing of subsoil. The subsoil was relatively unstable decrease. And second interesting point is this two SN curves. This curve was measured directly at the specimen, which was cut from the pipeline, and this specimen included the weld direct from this pipeline. And this is the steel X52, and this top curve is basic material from this steel X52, and this bottom curve is the curve from specimen with weld joint. It's possible to see notch factor, like a ratio between these two curves, yes, at the entire range of lifetimes. And it's possible to see that this notch factor is not constant in the entire range of lifetimes. Higher, this notch factor, higher value is at the high cycle region, and in the low cycle is relatively small. This is for material, also for steel X52, and this is for steel X60. Relatively similar, but not the same. It's the situation between these two curves. Yes, basic material and material with weld. It's very interesting that this notch factor is the function of number of cycles. And all conclusion and all assessment, how many cycles it's possible to exploit these pipes is in my conclusion. It's possible to read and it's possible to ask me. Thank you for your kind attention.
Thank you very much for your interesting presentation. Are there any questions from the audience? I don't see.
Congratulations for the very clear presentation. It's very interesting problem. I just fronted this kind of problem in several failures of kind of tubes. It's very interesting the fact that the maximum bending is going to increase in this monitoring that you had 3 years. So I will analyze the paper in detail. Thank you.
Good. Thank you, Giuseppe.
Thank you very much. I think we can skip to the next presentation.
Okay. Thank you, Dan.
Thank you again for your presentation.
Okay.
Okay, the authors of the next speech are Nobile, Panella, Pirinu, and Saponaro. The work is entitled The Bending Residual Strength of Damaged AL Foam Sandwich Through UT and IRT Analysis. I kindly ask to, I think it's Dr. Pirinu that share her screen and start the presentation. Okay, so when you want, you can share and start the discussion.
Okay, thank you. Did you see my presentation?
Yes.
Okay. Welcome everyone. My name is Alessandra Pirinu. I'm a PhD student of the University of Salento. I want to share with you the presentation Bending Residual Strength of Damaged L-foam Sandwiches through Ultrasonic and Infrared Analysis. Sandwich structure with aluminum foam core and GFRP skin combine lightness and rigidity in addition to advantage cost. And in the case of bending loads, the stiffness and strain increase rapidly with the thickness and density of a material constituent, and different breaking mechanism could arise during the service life. Recent studies investigate the effect of pre-existing damage on static and fatigue behavior of a composite structure. Therefore, in this research, static three-point bending tests are carried out on the 2 series of GFRP aluminum sandwich panels to compare the fractural behavior in absence or in presence of simulated impact damage. The experimental data results and the damage mode are analyzed in both impact and bending test. And in addition, phase diary ultrasonic and thermographic investigation are carried out for damage zone assessment, showing a size variability of impacted region due to non-uniform morphology and different foam density. Closed cell alulite aluminum foam of different thickness and glass fiber reinforced polymer laminates on a flat aluminum surface are used for the manufacturing of sandwich panels. In particular, the alulite foam are produced with the composition of particles method that release gas inside the semi-solid, and specifically, these foam are made by inserting in the extruded bars before expansion the foaming agents, and between two aluminum alloy plates, a hot lamination to form a sandwich with thin walls of aluminum alloy and a core made of aluminum and foaming agents is employed, and the end layout is employed for the lamination process with a subsequent vacuum bag to remove the air incorporated in the composite and the resin excess during the layout process, as shown in the second figure, applying a uniform pressure between the GFRP skins and the aluminum foam skins. A preliminary preparation of a metal surface is a fundamental operation for a good adhesion between the metal surface and the FRP laminates. The selected matrix is a two-component low viscosity epoxy resin, and as reinforcement, the 100 plain balanced and 160 twill balanced fiberglass are the selected fabrics for the lamination process of two final samples of two different thickness. And in particular, as reported in the table, an almost isotropic symmetrical lamination sequence is chosen for both sample series, and two layers of balanced fabric are employed because it offers a good uniformity in terms of stiffness and good resistance to crack propagation. As shown in the second figure, the manufactured sandwich panels are subsequently cut to obtain a batch of specimen to be tested. In particular, the MTS 810 model with a load capacity of 100 kilonewton is the testing machine system employed for the simulation of impact damage on AFS samples. It consists of a stainless steel sphere with 23 millimeter in diameter, as shown in the first figure. A flat steel base is placed on a lower grip of a testing machine to support the various specimens during the impact simulation test, while the impactator is gripped on upper grip. As shown in the second figure, the static 3-point bending tests are carried out using a different hydraulic model Instron 8516 testing machine with a load capacity of 250 kilonewton, and no specific regulation is followed to perform the test of simulated impact damage, while the indication of ISTM C393 standard method for flexural property of sandwich structure are followed for the bending test. The slide shows the results of impact damage simulation. The tests are carried out employing a constant speed of 110 millimeter per second, setting a depth of 4 millimeter as a depth for the impactor penetration into the specimen. The comparison of two batches of specimens show the force displacement diagram with the different data results that highlight the different density of foam influence the static behavior of impact damage. In fact, the batch of specimens are obtained in two different zones of panels. In particular, in the blue boxes, the batch of specimens are obtained from the edge of the laminated sandwich panels, and the red zone represents the specimen obtained in the central part of panels. In fact, the central zone are characterized by a lower but more homogeneous density with respect to the edge area, motivated the choice of obtaining the final specimen for the bending test in this sector. In the thick specimen, the presence of a higher density produce an evidence difference in impact force between the other one specimen. The impact is obtained in the central part of a specimen to avoid the detachment of skin near the edge and for a better inspection convenience with non-destructive control. The ultrasonic contact techniques is employed for inspection of impact damage of AFS specimen. The ultrasonic instrumentation consists of an Olympus with a 64-element phased array probe and 2.25 MHz of frequency. The unit probe and the mini encoder with a resolution of 12 steps per minute record the data, the ultrasonic data, synchronizing the acquisition with the linear movement. In addition, the infrared thermographic pulsed and the pulsed thermographic inspection are represent the second non-destructive technique employed for the inspection of impacted specimen. The infrared instrumentation consists of two halogen lamps of 1000 watt employed as thermal source, and the signal model flare A655SG microbolometric thermal camera is the thermal camera employed for the acquisition of thermal sequence. In particular, infrared and ultrasonic data analysis are analyzed in a MATLAB environment to compare the size evaluation of damage zone in sandwich structure. In particular, for the quantification of damage in terms of size and shape. The visual analysis of impact damage show a clear area of deformation around the impacted zone between the FS specimen. The analysis of impactor impression of a specimen involves a depth of a couple of millimeters near the laminate core interface. Then the C-scan maps were carried out between a 0 and 2 millimeters, and the short heating time of 3 seconds are employed for the non-destructive inspection. And for a better characterization of damage, the C-scan and the thermal maps were exported and manipulated in MATLAB environment, employed a suitable routine for the binarization of different experimental data, assigning a specific threshold value for a suitable evaluation of damage zone evaluated in the region of the interest in this case. And in particular, the method is employed for all impacted specimen, and the threshold values are computed by suitable evaluation of amplitude detected around the edge of impact area, where the amplitude varies rapidly and the defect is clearly identified. This allowed to process the image where the impact imprint is clearly highlighted and the external zone of specimen is manipulated for a clearly size evaluation. The C-scan and the binarized thermal maps are employed for the calculation of impact damage, and in particular, the procedure of binarization is employed for both non-destructive technique, and in this case, the estimation of impact area shows an evident difference of area, in particular between the two batches of specimen. Between the two specimens, the difference is due for the different deformation zone, because the IFS-20 are characterized by a lower density of constituent materials that determine a different strain and deformation of materials with the different deformated zones. But between the two techniques, seems that the thermography underestimates the size of impacted damage, with the exception of IFS-30 specimen. This could be motivated by the fact that the direct heat flow from the lamps and the surface of specimen seems don't affect the deformated surface. In particular, 12 specimens are tested in 3-point.
Alessandra,
Yes.
I ask you to speed up your presentation because we are a little bit late. So if you want to skip and show us the main results and the conclusion, I will be grateful.
Okay. So in this figure, I reported the load displacements curve obtained in bending test. And in all specimens, the initial in the linear elastic behavior is followed by elastoplastic phase until a peak value with a loss of load. The data analysis of damage mode are reported in this example slide, where the partial detachment of compressed skin and the breaking of stretched GFRP skin occur for almost of IFS-20 panels. But for IFS-30 specimen, seems that the indentation, the detachment, and the fracture of a core are the damage mode that could be arise. But in this case, the absence or the presence of impact damage seems not is the main influence for the damage mode as the density of material constituent. Therefore, the experimental and the non-destructive results highlight the influence of impact damage for the thin specimen, and the mechanical bending behavior seems to be very affected by the presence or the absence of the impact damage. So the non-destructive control on impacted specimen highlights the delamination zone identified by the deformation and the damage zone. The specimen are obtained for the bending test evaluation in absence or in presence of impact damage, and it seems that the presence of impact is very influenced in the case of the thin materials. Thank you for your attention, and excuse for the time.
Thank you, Alessandra. Don't worry. We know that maybe it's your first time, and so it's not a problem. We have no time to do a discussion about your presentation, but I ask to the participant if they have some question, they can use the chat and write directly to Dottoressa Alessandra Pirino. So let's continue with our session and move on the next speech. The authors are Zhen Wang and Andrea Manes. The intervention is entitled "The Investigation of the Biaxial Flexural Fracture of Aluminum Silicate Glass by Smeared Fixed Crack Method." I'd like to ask to the speaker to share, his presentation. When you want, you can start your discussion.
Okay, thank you. My name is Zhen Wang, and I'm a joint PhD student between Politecnico di Milano and Northwestern Polytechnical University in China. This is a combined experimental and numerical study on the biaxial fracture of aluminosilicate glass. For the experiments, we have conducted the bore-on-ring and ring-on-ring tests. For numerical simulations, the smeared fixed crack finite element method models were built to reproduce our experimental results, including the deformation field distribution as well as the fracture and failure modes of the glass specimens. For our experimental tests, we used a special designed fixture with a 45-degree mirror to help us to conduct the 3D DSA measurements so that we can obtain the full field deformation of the glass specimens. For numerical models, this is the models we built using the smeared fixed crack method. And we have calibrated some parameters very carefully, including the effect of integration points, effect of mesh size, and also the effect of the numerical loading speed used in our numerical models. Finally, this is our numerical results and experimental results. It can be seen that both the stress displacement curves and the displacement of the specimens at different stages during the loading process can be very well produced. This is the post-failure behavior of the glass plates. It can be seen that we have used 3 different kind of mesh types for our numerical simulation. And for the unstructured quadrilateral mesh and also the triangular mesh, the fracture modes of the specimens can be better reproduced. That's all. Thank you for your attention.
Thank you very much for your interesting and very briefly presentation. Are there any questions from the audience?
Luciana, may I speak?
Yes, Pietro, please.
Okay, sorry, the video was off. Okay, so thank you very much for your nice presentation. Just 2 very basic questions. So I saw that in the ROR situation, the strength is higher than, lower than in the BOR test. So I was just asking which is the difference between the 2 strengths evaluated. And the other thing, I saw that in your presentation, you mentioned that with respect to simulation, you have some fluctuation, which seems quite high. And so just I ask you some comments. That's all. Thank you very much.
Thank you very much for your question. For the first question, actually, both the BOR and the ROR tests are used to measure the biaxial flexural strength of brittle materials, basically. Actually, in our results, the strength by these 2 different methods is different. in my opinion, this difference comes from the defects in the material. Because for Bohr-on-ring tests, we can say it's like some indentation test. But for the Bohr-on-ring test, the loading fixture is a ring, so the stressed area is much bigger than this condition. So I think the difference may come from this place, because for brittle materials, the failure of the material is very sensitive to the surface defects of this material. And for the second question, you mean this fig is fluctuated or this one? Actually, this is the effect of the numerical loading speed, because in experiments, actually the loading speed is very low. It's quasi-static loading condition, but we can't apply that so low loading speed in numerical simulations. So we have to increase the loading speed, but we also have to get rid of the dynamic effect. So in this figure, there is some fluctuations in the strength displacement curves. But we have used the different loading speeds in our numerical models to find a good situation, which can both get some good results and also don't need so many calculation times.
Okay, thanks.
Thank you very much.
Thank you, Zen. We are perfectly in time, so we can move to the last presentation of this session. The speech is entitled "The Size Effect on the Apparent Tensile Strength of Brittle Materials with Spherical Cavities." The authors are Ciao Correas, Corrado, Sapora, and Cornetti. I see that Ciao Correas is ready, so when you want, please share your presentation and start the discussion.
Okay, 1 second, just I'm trying to, okay now. Okay, can you see my screen?
For the moment, no.
Okay.
Okay,
now
I think
okay.
now it's work. Okay, please.
Okay, perfect. Okay, well, so welcome. My name is Arturo Chao, and I'm glad to welcome you to this, let's say, brief presentation about the size effect on the tensile strength of brittle materials with spherical cavities. First of all, I would like to thank the co-authors of this project for their contribution, the Professor Mauro Corrado, Professor Alberto Sapora, and Professor Pietro Cornetti. And okay, let's go to the topic. Basically, the idea of this analysis was to study the failure of an infinite domain filled with a homogeneous, linear, elastic, and brittle material that contains a spherical void inside under uniaxial tensile conditions. In that conditions, we can use the stress field by Goodyear from a very long time ago, so 1933. But even though there's no crack, we cannot get through the, let's say, commonly used maximum stress criterion, we cannot get this size effect that, for example, you can see on the right side of your screen from the experiments by Bertolotti and Fulrath, where even for very, very low porosities, there is a clear effect on this pore size onto the tensile strength. And so other theories needs to be used, and we will present some of them like very quickly. First one is the equivalent linear elastic fracture mechanics, which is just an extension of the equivalent of the linear elastic fracture mechanics that allows for its use in uncracked bodies, okay? Next one is the theory of critical distances, which basically is a non-local stress-based criteria that includes the fracture toughness somehow indirectly through characteristic length, so-called Irving's length. Then the finite fracture mechanics, which is a couple stress and energy criterion that has been used lately for a lot of geometries successfully, and so it's something that we will also use here. And eventually the well-known cohesive crack model, especially in the Dugdale, in its Dugdale formulation, because we are going to use semi-analytical approaches. So these four implementations require from some input functions, which can be in terms of the stress intensity factor, on the stress field, and on the crack opening displacement. Basically, depending on the formulation you use, you would need some of them or all of them. However, for this geometry, it's a bit more complex, and there are no analytical, or at least exact analytical solutions. And so we used an approach already introduced somehow similar to by Fett in Theo Fett in 1994, in which you determine an approximate analytical solution by interpolating the extreme cases. So in this case, it would be that of a penny crack and an edge crack of when the radius is much smaller and much larger than A. And eventually also we introduced the Tada equation for relating the stress intensity factor and the crack mouth opening displacement, which is to be used especially for the cohesive crack model. Basically, using this approach, semi-analytical approach, you can see that you can get very accurate results in comparison with numerical implementations, for example, as you see in the image. And then just the implementation of the different approaches, you can see that all of them are capable of, at least to some extent, capture the transition between unvoided and large void solutions. Although in the meantime, it's a bit different. There's a bit of difference between them. And eventually, if we use compare with the experimental results by Bertolotti and Fulra from 1976, we can see that the fitting is quite good, although there is some scatter in the experimental data that precludes to say, okay, this formulation is better than the other one. Although, if we look at the lowest porosity case and the average of that, the average value of that porosity case, we can see that finite fracture mechanics average stress, which is the green line, is the one providing the most accurate result. And so basically, this is what we concluded out of this analysis. And yeah, I'm now happy to answer any question that you might have. Thank you so much.
Thank you very much for your interesting presentation. Are there any questions from the audience? You've shown in your experimental results that the scatter is quite high. Can you explain us the reasons that causes this quite high scatter?
Yeah, basically there are two reasons. For example, in these experiments, they were using sodium borosilicate specimens that are very brittle materials, and so they are really flow dependent. It's ultimate behavior. Moreover, there is also two more reasons in which the porosity was controlled, but obviously you cannot control the interaction between the pores in this case. Because it's not a single pore, and some source of scatter in that point. Then the pores were not of a fixed size, but instead within a range. So also there is one more reason of scatter. And the last one is that the conditions were in 4-point bending, and the pores could be close to the free edge. And so you have then there are also some free edge effects that you cannot capture with this formulation. However, overall, since there were a lot of experiments conducted, in overall we can get just a look at the average, because obviously it will be the most representative, and in that case we can see that the predictions are reasonably good.
Okay, so modifying the experiments, you think that this noise can be reduced?
Yeah, actually, yes. For the best option would be to use a material that is not so flow dependent, but still linear elastic until fracture. So that's something really somehow complex to get, and then to control the pore inside. But still, with these experiments, you can infer the accuracy of these methods.
Okay, thank you very much. I ask if there are any questions from the audience. We have 2-3 minutes more. Okay, I don't see any question on chat. So we have finished in very perfect time all the presentation of this session. I want to thank you all for your presence and for your active interaction. So I say to you goodbye and have a good lunch.
Yes, goodbye.
Thank you.
Have a good lunch.
Goodbye.
Goodbye. Goodbye.
Goodbye.
Yes. 5 minutes to start the session. Two minutes. Hello, everyone. And let's start the session number 11. We have 12 presentation today. We have 10 minutes for each presentation. The first presentation is entitled Fracture Assessment of U-notched PMMA under mixed mode 1-2 loading conditions by means of local approaches by Pietro Foti, Javad Razavi, and Filippo Berto. Please,
everybody.
Pietro.
Can you hear me?
Yes, Pietro.
Can you see my screen?
Okay.
Okay. Okay. I'm Pedro Podi, and I'm a PhD candidate at the Norwegian University of Science and Technology. And the work that I'm going to talk about today has been carried out with the support of the Professor Razzavi and the Professor Berto, that is my main supervisor. The aim of this work was to compare three different local approaches dealing with the fracture assessment of U-notched components made of PMMA under different loading conditions, and to assess the possibility to apply these methods with the coarse discretization, reducing the computational time required. One of the methods that has been considered in this work was the strain energy density method. That is a method usually validated to investigate both fracture in static condition and fatigue failure. During this short presentation, I want to highlight only a few details about this method. In particular, its low sensitivity to mesh refinement, that make it a method suitable for investigating the fracture assessment, the fracture behavior in both static and fatigue condition of complex components. And the volume-free procedure that has been applied in this work, that is simplifying the method and its application, even if with this procedure we are going to lose a bit of the mesh with the low mesh sensitivity of the method, because the accuracy of the evaluation of the SD value is now dependent on the mesh discretization, because we are going to approximate the integration domain. But we have evaluated the error in applying this procedure, and it is overall acceptable because of the reduction of the effort to apply the method. The other methods that has been applied in this work are the theory of critical distances, in particular in its point method and line method version. And the basic idea of this method is that that fracture may be assumed to occur when the stress, defined in different ways according to the different TCD versions, reached critical values that is named the inherent stress. As we can see from the drawings, there are different ways to apply the theory of critical distances. And in particular, in this work, we applied the point method and the line method. In this slide, you can, In this slide, you can see the specimens geometry considered, that is allowing us to consider the different contribution of mode 1 and mode 2 loadings with changing the beta angle in figure. And we considered for as the material properties data from literature in order to can carry out the numerical simulation to apply the local approaches considered in this work. You can also see here the static test results together with the whole specimen tested. In this work, two numerical models were considered. The one above is the most refined one, and it is the one that should lead to the to as low as possible errors in the evaluation of the stress field, and to as low as possible approximation in the control volume shape that results in a low approximation of the SD value. While the model presented below is a very coarse mesh model that has been used also in this work. Here you can see the results of the whole work, and as a conclusion, we can say that all the three different methods considered in this work can summarize the experimental results in a unique scatter band. We didn't notice any clear difference between with changing the loading mode or also the notch notch radius, and all the methods show the comparable results with the changing in the mesh refinement, as you can see from the diagrams that I reported in this slide. Thank you for your attention.
Thank you, Pietro. Any questions? No one? So Pietro, I have a curiosity seeing your work. You consider 3 different methods to describe the same effect and showing almost the same results. Which are the actual differences between them? And is there an optimized method between them to better describe the failure?
And optimized? I didn't hear the second part of the question.
Yes, which are the real differences between the efficiency of investigated methods?
Well, the SED method is based on the evaluation of a parameter that is evaluated in the finite element model through the nodal displacement and the stiffness matrix. So we are sure that this parameter is very stable, also with very coarse discretization. While indeed the problem that we have with applying the volume-free procedure is not about the approximation or possible errors coming from the finite element model in evaluating the strain energy density, but we are introducing an approximation on the domain in which the volume, the strain energy density is considered. While the TCD method and the TCD method is based on a value that is dependent on the that has to be evaluated through the stress field that is on the other hand dependent on the mesh refinement. So we are expecting a bit in this case we didn't notice a huge difference between a very refined model and a model with a very coarse discretization. But if we are going to notch radius very low, we can have an higher error in estimating the value that is considered as a critical value from the TCD method, because we are considering the stress field, and as we all know, with the zero radius, we should have the stress singularity, and so we should expect a greater error in evaluating this stress. Even if it is worth saying that we are not evaluating the stress at the notch tip, but we are evaluating the stress at a certain distance. So it should be assessed if the stress at that particular distance is so dependent on the mesh refinement, or it gives reasonable results, acceptable results.
Okay, Pietro, thank you very much for your speech. And let's move to the next presentation. The title is Prediction of Fatigue Regrowth Using a Damage Model. And the authors are Sergio, Borges, Neto, and Antunes.
Hello, can you hear me?
Hi, Sergio.
Okay, so I'm going to share my presentation. So you all can see the presentation?
It's all right.
It's all right. Okay, so we are from University of Coimbra, and this work is based on the implementation of the well-known GTN damage model on the previous existent node-Ruiz numeric model used to predict fractic crack growth rate. So I just want to make a small presentation and say that we believe, the authors believe that the true way to understand the fatigue phenomenon is to study the mechanisms acting at the crack tip, and namely the plastic strain and the damage that is carried with itself, and of course also the crack closure and other mechanisms as residual stresses and oxidation, etc., etc. So I want to highlight the results of the study, that is the implementation of the damage model as two different behaviors depending on the delta K. For lower the delta Ks, the GTN damage model induces a protective behavior, reducing the ADN. But for higher delta Ks, this behavior is inversed, and the GTN gives higher ADN values. And then we studied the reason behind these strange behaviors, and we found out that, as you can see in the work, that crack closure is the main mechanism to blame for these behaviors and for the inversion that occurs, because the porosity and the reduction of properties of the material that is induced when we introduce the GTN damage model carries out more plastic strain, and then the more plastic strain induces more PICC, resulting in higher levels of crack closure. What happens for higher delta Ks is that we suffer some strain ratcheting phenomenon, and as the crack closure is reduced, the higher plastic strain then carries more DADN due to the fact that our node release numeric model works with the critical plastic strain. So I don't know if you have any questions.
Thank you, Sergio. Any questions from the colleagues, online colleagues? No one? So Sergio, I have a curiosity. You said that high values of plastic strain in high values of the closure decrease the propagation ratio, decreasing the fragility. I would like to know a few words about this concept, because the definition of fragility isn't the RDN ratio.
Yes, of course. But what I said is that.
Can you tell me?
I'm going to explain it.
Can you tell us
as
how?
I can? Yes, of course. What I said is that for higher values of delta K, there is more plastic strain, and it's obvious. And as our numeric model works with the critical plastic strain, as the crack closure suffers some strain ratcheting and its protective behavior ceases, the critical plastic strain is reached sooner, and of course that the DADN is higher for higher values of delta K with GTN, as you can see in the pictures. Of course that it has nothing to do with fragility, but the introduction of porosity reduces some of the mechanical properties of the materials, of course.
Okay, thank you very much. Other questions? No one? Thank you, Sergio. And let's move to the next presentation. The title is Fracture Behavior of Reactor Steel 20 Magnesium Molybdenum Nickel 55 in the transition temperature region. Authors are Dordovich, Petrovsky, Sedmak, Kozak, and Samardzic. Please. Is there an author of this work? No. I recall it in the next time. So next presentation one is entitled Fracture Criteria and the Duality of Critical Damage Failure Transitions. Oleg Naimark is the author. Oleg, are you online? Hello.
Okay, yes, I'm here, but I have some problem. Okay.
Okay.
Did you see my presentation or not?
Not now.
Okay. I have some problem. I'll try to.
Which kind of problem? Please start the presentation and then click on the green
Yes,
button.
I do that,
No?
but
and choose the window to share.
But it's not success.
Success? No problem, because we have a time.
Strange, but I could not do that. I am sorry, but I have some technical problem.
If you need some time, I can move to the next presentation and we will try to.
Yes, maybe we could restart. Okay, okay. I will try to do one time.
No
yes,
problem.
Thank you.
No
After
problem.
that, maybe. Okay.
Yes. So the next presentation, the title of next presentation is The Effect of Surface Defects Interaction on the Strain of a Pressurized Spherical Shell by Sedova, Uklova, and Pronina. Many authors. The work is The Effect of Surface Defects Interaction on the Strain of the Pressurized Spherical Shell. Okay, next one again. Next work is Effect of Dispersed Particles on Titanium Aluminium Alloys Fracture Behavior. Authors are Mondal, Filone, and Felli.
Yes, I'm here, Professor. I would like to share my screen.
Hi.
Hi, Professor.
Please.
Yes. A moment, please.
Yeah, yes.
Yes, so.
Oh, okay.
This work
Please.
is based upon the effect of dispersed particles on TIL alloys fracture behavior. For this research, we considered two kinds of alloys, TIL alloys, one with alumina dispersion and one without alumina dispersion. The one with alumina dispersion had 3% of volumetric alumina inside it. Here are the two micrographs showing the grain structure of both the alloys. As you can see on the lower picture that there are few black dots which represent the alumina particles in it, but both the alloys have similar kind of lamellar structure with alpha 2 and gamma grains, and as well as gamma grains within it. Coming to the fracture surface of the base alloy, here you can see the macroscopic fracture surfaces. The two on the left side show the alloy alloy without alumina dispersion, and the picture on the right shows the alloy with alumina dispersion. As a general look, we can see that the alloy is very brittle, while the one with alumina dispersion seems to be much more brittle than the other alloy. Coming to the fracture surface of the alloy without alumina dispersion, we can see that the fracture surface is a typical cleavage fracture due to the brittleness, which is translamellar and transgranular in nature. Okay, there are also some cavities present in the casting. And coming to the fracture surface of the alloy with alumina dispersion, this also has the same kind of fracture behavior, that is cleavage fracture with translamellar and transgranular a type of fracture. But the interesting thing is that we can see some alumina concentration which are marked by the circles at the fracture lines. This is because of the dislocation of alumina from its point, making a hole, again represented by the triangles, and coming to these points of fracture. So there has been a dislocation of alumina inside the metal matrix. There are also some micro cracks inside the metal matrix, which is represented by the rectangle over here. One more interesting thing that we noticed about the alloy with alumina dispersion is that there has been some, the number of shrinkage cavities inside the metal matrix is more than the one without alumina dispersion. And there are also some typical crystal structure inside the cavities, which are probably due to the addition of alumina in the metal matrix. So we can finally conclude that the dispersed alumina hardens the alloy. It increases the mechanical properties of base TiAl alloy, but that is done at high temperature. But it also affects the fracture behavior of the alloy, and the presence of dispersed particles also represent a discontinuity in the metal matrix, which again favors the crack propagation and increases the brittleness of the alloy, especially at room temperature. And a further study is required to optimize the shape, quality, and distribution of these dispersed particles with the aim of increasing the fracture toughness of these kinds of alloys. Thank you.
Thank you, Abhishek. Any question? So, Abhishek,
yes.
Please, can you show the scanning electron microscope pictures, the last one and the previous one?
Yes. Yes.
Thank you.
This?
This, excluding the shrinkage, the previous one more.
This one? Yes.
Here, okay. This is the fracture surface morphology due to alumina dispersion, dispersion. Okay, dispersed. Yes. And the previous one is taken without
alumina dispersion.
Okay, I don't see the very big differences.
Yes, they are not. It is not a very big difference in their appearance, but the difference is only. The type of fracture is similar in both of them, but the difference is only because of the presence of alumina. As you see, the circles, there is a concentration of alumina at these points, which is not in the other alloy. So this proves that there has been a dislocation of alumina at these points from the other sites.
Okay. Okay. And which is the real contribution of the alumina dispersion in the matrix? Is there any kind of bonding between alumina and in the matrix or not?
So yes, there has been some, Professor. But the effect of adding alumina is only seen when it is activated at an temperature above 500 to 600 degrees Celsius. At that temperature, alumina is highly helpful in increasing the mechanical strength of these kinds of alloy. Which again is, these alloys are supposed to work at a temperature above 700, in the range of 700 to 1200 degrees Celsius. So at that temperature, alumina is highly effective in increasing the mechanical properties, but it has a disadvantage that at lower temperature, at room temperatures, this also increases the brittleness of the alloy.
Thank you very much, Abhishek.
Yeah, thank you so much, Professor.
Any question from the colleagues? No one? Thanks, Abhishek. And
thank you so much, Professor, for your time.
Okay. It's my pleasure, Abhishek. Oleg, are you ready to share the presentation, or do you need some time again?
I'm sorry, but where is I have still problem.
Okay, I can move to next presentation one, no problem.
Okay.
Take your time, no problem. Okay.
Daria Akulova is ready.
Next presentation, Yulia.
Yeah. Hi, Daria Akulova is
Yulia.
ready.
Which is the title of your presentation, Yulia?
Daria, where is you?
Oh, yes, Akulova and Sindova is ready for short presentation on the effect of surface defects interaction. Sorry.
Okay.
I didn't answer.
So, Yulia, the title is The Effect of Surface Defects Interaction, the Strength of the Pressurized Spherical Shell. It's correct? Please, Yulia, do you want...
Sorry, Daria, share your screen. Daria Akulova made a presentation.
Okay.
Daria, share your screen.
Okay, okay.
Do you see my screen?
It's right. It's okay.
Thank you.
Please, Yulia.
Let me present our study. We studied the effect of multiple surface defects interaction on the stress state of the spherical shell under internal pressure. The defects are assumed to have a form of hemispherical notches uniformly and randomly arranged on the equator of the sphere. We also consider the effect of smoothing, which is observed in case of corrosion. Two cases with different numbers of notches are investigated. Linearly elastic model and elastic plastic model with linear strengthening. We found that for evenly spaced defects, the maximum stress is observed for a relatively small range of varying the number of defects, while for the random distribution, maximum is observed for a noticeably larger range of numbers, as you can see in these figures. We've also confirmed that the maximum stress is observed when the adjacent notches either slightly overlap or there is a small distance between them. Distance between them and the max. Resulting in sharp edge. Considering geometries with only two notches showed that increase with decreasing distance, the stress increase with decreasing distance between the centers of notches is observed only up to a certain critical value of the distance. After reaching this value, the stresses begin to decrease. Also the dependencies of the maximum stress on the number of defects are qualitatively the same in cases of linear elastic and elastic plastic problems. However, the stress concentration in the elastic plastic model is lower than the case of the pure elastic model. So this is all I wanted to say in my short presentation.
Thank you very much, Yulia. Any question from the colleagues? So Julia, I have just a curiosity for you. You said that the maximum stress of defects density is the same both in elastic and in plastic zone. Can you tell us
Yes.
some words about this? Why? Because why? Which is your opinion? Which is the phenomena which is to the base of this your results?
I can answer that. I can suggest that the density of the stresses depend on this on the same characteristics such as number of defects and the length between the centers of defects and their interaction, and these characteristics are the same in the linear elastic model and elastic plastic model. So.
Because in the plastic zone sometimes the triaxiality changes and the maximum stress sometimes cannot be the main driving force for the phenomena developing in this range. Have you an idea? Because you found that the stress defect density maximum stress is the effect is the same in elastic and plastic zone. Which is your opinion?
So I said that not the same, but the nature, or I can.
Okay.
They are qualitatively the same, but
it's not the same, but changes.
Changes
the importance.
Same manner.
Okay, great. Thank you, Julia. Any question? Any other questions for Julia? No one? Thank you very much, Julia, and my compliments for your presentation. So let's move to the next presentation one. The title is Influence of the B material interface on the crack propagation through the thin protective layer by Malikova, Mayarka, Dubek, and Seitler. Is there a presenter for this work? No? Let's move to the next one. The title is Numerical Prediction of Transverse Cracking and Delamination in Fiber-Reinforced Laminates by using a two-scale cohesive finite element approach by Gaetano, Greco, Leonetti, Lonetti, and Blasi.
Hello,
Prego.
everyone. Thank you, Mr. Chair. I'm going to share my presentation.
Please.
Okay, can you see it?
Yes, yes, Lorenzo.
Okay. Hello, everyone. Again, I'm Lorenzo Leonetti from University of Calabria. Well, in this work, we have presented a novel two-scale cohesive finite element model for the failure analysis of periodic composite structures. So this model combines two main ingredients. The first is nonlinear continuous discontinuous homogenization strategy, and the second one is a cohesive volumetric finite element approach. So in this way, combining these two ingredients, the resulting nonlinear macroscale model is enhanced with interface elements embedded in a classical bulk finite element mesh. And these elements are equipped with a microscopically informed traction separation law. So after a proper repeating unit cell is defined for the given microstructure, the proposed numerical model is divided in two steps. So in the first step, a classical linear homogenization is performed to obtain the undamaged elastic moduli of the given composite. And then in the second step, a nonlinear homogenization is performed along a given macrostream path involving mode 1 fracture propagation. So in this step, so the aim of this step is a double aim. So computing both the bulk damage properties up to strain localization, and then the interface fracture properties in the softening regime. So we assessed the reliability of the proposed two-scale model by performing several validation tests on a fiber-reinforced metal laminate loaded in tension and subjected to transverse cracking and induced interply delamination. Moreover, we used a rigorous sensitivity analysis to demonstrate the mesh size independence of the related numerical results. And finally, as a further validation step, suitable comparison with a direct numerical simulation performed on a fully meshed model have confirmed that the present two-scale model exhibits very good accuracy and computational efficiency in predicting both the overall load carrying capacity of the composite and the related crack pattern, as you can see. Thank you for your attention.
Thanks, Lorenzo, and my compliments for your work.
Thank you, Mr. Chair.
Any question? So, Lorenzo, just a curiosity, because I try more and more times to simulate the crack propagation using your software. I see you use COMSOL multiphysics plus MATLAB.
Yes, exactly.
How it's possible to generate the cracks using COMSOL multiphysics? Having
Sure.
a conversation of the calculus.
Okay. Obviously, COMSOL multiphysics is not intended for simulating cohesive cracks in a diffuse manner, like in this work. So we have used MATLAB to take an automatically generated mesh and decoupling the nodes of the mesh boundaries in an automatic manner by using an intrinsic feature of present inside the COMSOL multiphysics. There is a special interface element. We used it in combination with the script to place this element in along the interface generated with MATLAB. So we use a combined approach in this sense. So there is a little effort of scripting in them, but it's not impossible. It's a bit tricky, but I can show you some details maybe in private if you like, if you want to some detail. But we use an automatic mesh and a script to explode it and insert this element. Just the last thing that we inserted a novel weak formulation to enforce the irreversibility condition of the cohesive element by scripting, by using the scripting capabilities of the COMSOL multiphysics. You know, you can define a new physics with other equation in the weak form. So we inserted a new principle of vector work taking into account an additional term and also another additional term taking account of the reversibility. So that's all.
Thank you, Lorenzo, and my compliments for your work.
Thank you again.
The problem, one of problem of this software, and that it have not some methods like element vanishing in order one to simulate cracks and so on.
Yeah.
And we have to formulate models, complicated models using MATLAB as a component of the multiphysics, causal multiphysics. Thank you very much. Any questions?
Can I?
Please, Costanzo Bellini.
Thank you. Just a curiosity, which is the gain in terms of computational time or other stuff in by adopting this new methodology for the simulation?
Okay, for sure, the main aim of a multi-scale model is to gain a good accuracy and in the same time computational efficiency. With our method, we highlighted a speed up of about 80. So our method is 80 faster than the direct numerical simulation. Of course, a direct numerical simulation has the advantage of capturing the local stress gradient and strain gradient inside the computational domain, let's say this composite. But if one is interested in the global behavior, a faster simulation is sufficient. So just to speak about computational times, the direct numerical simulation required 18 hours. Our method required only 12 minutes. So a very good improvement of computational times.
Okay, thank you.
Thank you to you.
Thank you again. And let's move to the next presentation. The title is Analysis of the laminated multi-layered functionally graded viscoelastic beam by Rizov. Professor Rizov is online. No. So the next presentation is entitled Topology Optimization and Fatigue Analysis of a Lifting Hook.
Can you hear me?
By Teke. Yes. Please,
Hello.
Ibrahim.
Hello.
Hello.
I will share the screen first. And can you see the slide presentation?
Perfectly.
Okay.
Perfect.
I'm Ibrahim. I'm attending from Bursa Technical University, and one of the authors, Ahmet Hanifi Ertaş, the professor of that university, is my thesis advisor. And I'm here to introduce this study, Topology Optimization and Fatigue Analysis of a Lifting Hook. So let's get started. First of all, the model is here and the boundary conditions are shown. Loading capacity is 5 tons and it is fixed at the shaft. And after that, under static loading, topology optimization study made. And after the topology optimization, we generated 3 different models. And with these 3 different models, we made static analysis, and results shows the third one is the most appropriate because the stress values are slightly better, or we can say as the same as the original one, and minimum fatigue life is slightly better according to stress values. And first and the second one, we don't have to consider them here. And also our main goal was a lightweight model, and we achieved it. The third optimized model is 285 grams less than the original one. For the last sentence, fatigue life result of the third model is here, and the minimum fatigue life is reached at the maximum stress area. Thank you, that's all.
Thank you, Ibrahim. Any question? So, Ibrahim, just a curiosity, have you calculated the positions of the neutral axis of your investigated hooks?
Actually, we used ANSYS program, and with we didn't consider that the neutral axis for this study. Yani,
where are positioned the neutral axis in both of the hook shape?
Neutral axis
on top of the shaft.
Neutral axis on top of the shaft. Evet. Yeah, sorry. Are you asking the load center, or what?
Yeah.
Did you ask?
Oh, okay. And I think it's not so easy to calculate the position of this axis. Can you tell us some words about the algorithm you used for generates the different shapes of the hooks?
Actually, density-based method we first used here, and after the optimization, I generated them manually, not with a according to this result I created them. And actually, for the at the back of the opening hole at the back of the load center, and to the near at the back of the maximum stress area, to see it is not it will not give a verify to it will not give a result.
Thanks, Ibrahim.
Dear Chair, let me give you a few sentences related to this study. First of all, this is an ongoing project, so this presentations covers just the first results. Of course, optimization, for optimization technique, we use topology optimization, and for topology optimization, it's not possible to obtain directly smooth surfaces, as you know. So, so after obtaining the results, of course, my students used space claim and try to obtain smooth surfaces. And this kind of surfaces occurs on center of the stresses, which have a minimum values comparing with other parts. So we are trying to use different techniques, different optimization technique, and maybe in a couple of weeks later, we will finish and we will get the final results. So this is the just previous and first results covers. So our aim is to find a lightweight hook in order to improve both economical point of view and at the same time fatigue life of the structure. That's all.
Oh, thank you very much for the
you are welcome.
The answer. So no other questions? No one? And let's move to the next. Sorry, Oleg, are you ready to present your work? if you want, you can present without any slides if you want. Oh, perfect, perfect, Oleg. You have to switch on the microphone, Oleg. Your microphone. You have to switch on. The icon of the microphone is in lower side on the left. Okay.
Okay. Now you have. You hear me or not?
Very well. It's already.
It's okay. Maybe now I could just explain the main idea, yes, of my presentation. Is okay?
It's okay. It's okay. Please do.
It's okay. My idea of my presentation is the following. We have the feeling that there is a really fundamental problem concerning nature of criteria. For instance, if we have stress intensity factor, the background for this criteria after Irwin is the existence of self-similar solution of the stress field as a corrective. Okay. If we consider, for instance, situation when the behavior of materials in condition of fatigue or dynamic of crack propagation is related to formation of the process zone, we are trying to link the property of materials in the process zone with some characteristic stress or energy in the cohesive area. But if we consider, and it's maybe one of the consistent of our results, the collective behavior of defects at the corrective zone, we could find that there is also self-similar solution which is responsible for generation of the process zone. This solution also has singular nature, because collective behavior of defect, for instance, in the case of the plasticity in the correct process zone, could form the area of localized plasticity with some specific behavior of defects. In the case of quasi-brittle materials, it's the area of damage localization, also with very specific type of criticality as specific similar solution. It means that interplay between two kinds of self-similar solution with singular nature responsible for stress intensity factor or generation of crack tip zone could be responsible for different scenario of crack propagation in the condition of crack fatigue or dynamic crack propagation. But it's also very important for the case when the damage accumulation stage could have maybe more duration than crack advance. And in this case, the knowledge about characteristic self-similar solution concerning damage accumulation could be very, very important for the prediction of lifetime. And especially according to our feeling, and it was the variant of demonstration in my presentation, it's very important in the case of, for instance, gigacycle fatigue or very high cycle fatigue, because damage accumulation stage in this case very, very pronounced in comparison with crack advance. And when we compared, for instance, the scale invariance characteristics responsible for crack initiation, small crack initiation, crack advance in the condition of very high cycle fatigue, we established characteristic invariance responsible for collective behavior of defects, cracks process zone generation, and to derive macroscopic equation. And it was the way we considered it the way to explain, for instance, the power exponent in the Paris law. Why, for the case of plastic materials, we have close to 4, but for quasi-brittle material, we have the very sharp increase of this power. And according to our feeling, the reason is specific self-similar solution, which are responsible for formation of different kinetics of defects in the crack process zone. And it was illustrated by several our experimental data and also fracture analysis from point of view of rafters evolution in terms of invariance. And we propose some kinetic equations which link the crack advance with scaling invariance in the crack process zone. Yes, it's all.
Thank you very much, Oleg, for your presentation. Questions? Please, no one?
Thank you very much for your tolerance.
Thank you to you. I have just a curiosity.
Yes.
I see your work and you well describe the importance of damage failure transitions in a very high cycle fatigue in the way to predict the fatigue life. These kind of defects are small cracks and fish eyes and so on. In presence of different defects like pores due to sintering material and etc., your formulation is able or not to describe the fatigue life of the component?
Yes, thank you very much for your question, because especially for very high fatigue, and I think theoretical results and also results of structural study and experiment showed, according to my feeling, a very important question that there is a different type of singularity in solid with defects. The first time singularity is related to self-similar solution responsible for stress intensity factor. But if, for instance, crack advance could be sensitive to some damage accumulation in the process zone, for instance, I think it's very important that damage accumulation must reveal also the sign of singularity, because only singularity responsible to be comparable with stress singularity. It's the reason. And when we established specific singularities for damage evolution, it was the way to link different stage of damage accumulation, small crack nucleation, transition from small crack to Paris crack, and Paris crack advance according to self-similar law after Paris, because it's very important that starting from seminal work by Paris, that universality of the power exponent is the key point that needs to be explained from point of view of scaling phenomena due to the damage accumulation. It's my response on your question, maybe too long.
Thank you very much. It's exhaustive answer. Thank you very much. Any other questions? No one?
Yes.
Thank you, Oleg.
Thank you very much.
And the next presentation is, just a moment, I have to see the scheduled, okay, I have to ask the previous one, fracture behavior of reactor steel 20 magnesium moly nickel 55 in the transition temperature region. Is there some authors? Dorevich, Sedmak, Kozak, Samandrich? No one. Influence of the B material interface on the crack propagation through actin protective layer by Malikova, Miarka, Dubek, and Seitler? No. And analysis of the laminated multilayered functionally graded viscoelastic beam by Rizov.
Yes, I am.
Please, Professor Rizov.
Okay, I am going to share the screen.
Oleg, can you switch off your shared screen?
Okay.
Yes, the previous speaker.
Thank you very much.
Okay.
Please.
Where is it? Okay, one moment only. Can you see my screen?
Yes.
Okay.
I see the Explorer.
The Explorer? Oh, it shouldn't be the Explorer. Okay, I have to look what's the reason for this, because I opened the file on my screen. What's the problem? I will try again. Now, can you see the screen? My paper?
Perfectly. It's okay.
Okay. Okay. The lamination of a multi-layered, functionally graded cantilever beam configuration that exhibits linear viscoelastic behavior is analyzed in terms of the strain energy release rate in my paper. The lamination crack is located arbitrarily between the layers of the beam. The material in each layer is functionally graded along the width of the layer. The viscoelastic behavior of the material is treated by using a linear viscoelastic model that consists of two springs and a dashpot. In each layer, the modulus of elasticity of the springs and the coefficient of viscosity of the dashpot are distributed continuously along the width of this layer. A time-dependent solution of the strain energy release rate is derived by considering the strain energy accumulated in the multi-layered beam. The solution derived holds for beam made of layers which have different widths and material properties. Also, the number of layers is arbitrary. The solution derived is verified by applying the compliance method. The time-dependent solution is used to study the variation of the strain energy release rate with time due to the viscoelastic behavior of the material. The analysis indicates that the strain energy release rate increases with time. The influence of the delamination crack location along the width of the beam on the strain energy release rate is also analyzed. Concerning the effects of the material gradient along the width of the layers, the calculations show that the strain energy release rate decreases with increasing of Q11, Q21, and Q31. These parameters, Q11, Q21, and Q31, actually control the material inhomogeneity along the width of layers. The investigation reveals that the strain energy release rate decreases with increasing of E1L2 to E1L1 ratio and with increasing of E1L3 to E1L1 ratios. The increases of eta L2 to eta L1 and eta L3 to eta L1 ratios lead also to decrease of the strain energy release rate. The results obtained in this paper give information about the effects of location of the delamination crack, material inhomogeneity, and the external loading on the delamination behavior of the multi-layered functionally graded viscoelastic beams. The beam under consideration is shown in figure 1. This is a multi-layered beam with a delamination crack. The cross-section of the right-hand delamination crack is shown in figure 2. The viscoelastic model that is used in the present study is shown in figure 3. The model consists of 2 springs and a dashpot, linear springs and a linear dashpot. This is a linear model. Two 3-layered beam configurations are shown here. These configurations are analyzed in order to evaluate the effect of the delamination crack location along the width of the beam. The solutions to the strain energy release rate that which are derived in this paper are used to evaluate the effects of various factors and parameters on the strain energy release rate. Figure 5, for example, shows the strain energy release rate plotted against the non-dimensional time. Two curves are shown. These curves, curve 1 is actually the two curves are for different locations of the delamination along the beam width. Figure 6 shows the strain energy release rate plotted against Q11 parameter. 3 curves are shown here for 3 values of the parameter Q21. We can see that the strain energy release rate decreases with increasing of these parameters, Q11 and Q21. Actually, these parameters, they characterize the material inhomogeneity along the width of the layers. Figure 7 shows the strain energy release rate plotted against Q31 parameter. Again, here 3 curves are shown for different values of the parameter V phi. One can observe here that the strain energy release rate decreases with increasing of the parameter Q31 and with increasing of V phi. Figure 8 shows the strain energy release rate plotted again E1L2 to E1L1 ratio for 3 values of E1L3 to E1L1 ratios. The curves in this figure indicate that the strain energy release rate decreases with increasing of these ratios. Figure 9 shows the strain energy release rate plotted against eta L2 to eta L1 ratio. 3 curves are shown for 3 eta L3 to eta L1 ratios. And we can see here that the strain energy release rate decreases with the increasing of these ratios. This is my presentation. Thank you for your attention.
Thank you very much, Professor Rizov. Is there any question from the colleagues? Please, no one? So, Professor Rizov, and how do you take into account the real stress at the crack tip during the delamination damage?
Actually, in this paper, we use the beam theory, and we actually derive a solution of the strain energy release rate. And in fact, we don't account for the stresses in the lamination crack tip. We consider we use the strain energy accumulated in the beam to derive a solution to the strain energy release rate. And actually, this approach, the approach that is based on the consideration of the strain energy accumulated in the whole beam, is used also by many other authors when they derive solutions of the strain energy release rate for different delamination problems in beam structures.
Thank you very much, Professor Rizov.
You are welcome.
Other questions? No one? Thanks again. And I recall the previous colleagues, fracture behavior of reactor steel, 20 magnesium, moly, nickel, 55 in the transition temperature region. Is there any author? No. Another one is influence of the beam material interface on the crack propagation through a thin protective layer by Malikova, Miarka, Dubek, and Seitler. No. So let's move. The next presentation is a cycling model for a nickel titanium shaped memory alloy. and the author, it's me. Okay, just a moment. I try to share my presentation. Can you see my screen? Hello?
Yes,
Can you see my screen?
Yes.
Yes? Yes, thank you very much. So this work born from necessity to better interpolate and predict the real phase composition of a shape memory alloy. I remember that this kind of shape memory alloy is characterized by two different elastic regions. The first one and the third one, where in the first one we have phase named as austenite, but is not the same austenite of the steel, because this is a nickel titanium material, nickel titanium alloy. And the last one is a martensite, characterized by two different lattice. The first one is a cubic, the last one is monoclinic. And the second stage, in the second stage, we have a changing of a structure from the austenite site during the loading, and in a reverse way, we have a recover from the martensite to austenite to the original structure. And this is the cause, the reason of the memory shape. We analyzed by diffraction analysis the changing of the microstructure. Here you can see the austenite spectrum, and here the position of the atoms in the austenite lattice. And here you can see the spectrum of the martensite and the schema of the position of the atoms. So we proposed a very easy model to correct, calculate and predict the quantity of austenite and martensite, minimizing the differential of the energy potential, which depends on the deformation epsilon, the quantity of austenite, the quantity of martensite. Here is posed in a differential form, and then with the calculus of the minimum of this energy, the results carried out two equations. The first one, you can see that the quantity of martensite depends on the deformation epsilon. It depends from the coefficient C and D. In the same way, we have the quantification of the austenite. As we demonstrated in our work, the parameter C takes into account the cycling. In this case, at the first cycle, we can see that the parameter C is always the same. This is 1 in loading and loading conditions, but the parameter D changes in loading or in loading condition. It means that C takes into account the cycling and the effect of the hysteresis in loading and loading conditions. In this case, we parameterized the C. We discovered the C parameter in the cycles. We performed series of cycles from 1 to 100. Here we can see the variation of the parameter C, and the parameter D is always the same in the loading and loading conditions. Results are this. Here you can see the experimental results in the green, and in the red you can see the model results at the first cycle, at the cycle 10, here at the cycle 50 and 100. So this is the conclusions. I'm ready for your questions. Any question?
Yes, from me, it's possible. So you carried out some experimental tests, and which was the loading rate that you used, and if this loading rate is if there is a correlation, a possible correlation between the loading rate and the obtained result.
Yes, thanks for the two questions. The rate is very important because it changes the mechanical behavior, and when a material is able to change the microstructure, the dynamic of the changing, which involve the movement of the mass, like protons and atoms in general, is important. In our experiment, we used a quite low rate. Epsilon rate is, if I remember well, is around of 10 power minus 6. Yeah, so seconds power minus 1. Okay.
Okay. And another curiosity.
Other questions?
Another curiosity, if it is possible. I saw that the specimen is very small. The specimen that you used for this test is
Can you
very
repeat,
small.
because we have Professor Bellini, can you repeat please, because we have a stop of the line.
Okay. The specimen that you have used is very small. And how can this influence the result? Usually specimens are for tensile tests are bigger.
Oh, thank you very much. And yes, the specimen is small because is around 16 millimeters as a calibrating length. This is due to necessity to put the specimen inside the diffraction camera of a diffractometer, because the instrument is limited in the power, X-ray power, and in the volume to analyze. Which is the dependencies of mechanical properties to the dimensions? It's a good question. I don't know. I think cell parameters, not cell parameter, the diameter of the grains, structural grains, are very low. It's a nano-structured material. In this case, the dimension of a small specimen, I think, is not so important in order to influence the mechanical properties, I hope.
Okay, thank you.
Other questions?
I'm sorry, Alec Neumann, may I also ask, because I understand that presentation, I understand that presentation was very short, but if we are talking about shape memory alloys, it's very important to estimate the ranges of temperature when this kind of the alloys could reveal the shape memory effect or superelasticity. And what about temperature conditions that you realized your experiments?
Please, can you repeat slowly the last part of the question, because
yes,
I have a problem with the line.
In the case of study of mechanical behavior of shape memory alloys, it's extremely important to estimate the range of temperature when this kind of the alloys could reveal the shape memory effects or superelasticity. And what about characteristic temperature that you realized in your experiments?
So if I catch well, the question is what kind of energy I used to formulate the changing of the structures?
My question concerning characteristic temperatures. Characteristic temperatures are related to
the temperatures. Okay, okay. Yeah, yeah. The temperature, obviously, because we have no temperature. I think use a very low traction machine, but a patented traction machine, motors and the device are moved by a mechanism without any interactions. And the temperature, I think, is constant due to the low rate of movement of the rosette. And then, in order to take the spectrum in different deformation, we stopped during the cycling the device under load in order to form the X-ray diffraction directly on the material under load. Okay.
Yes, understand.
This is the only way. I hope that the temperature was constant. Shape and memory alloy are strongly influenced by the temperature.
Yes, of course.
In this case, we used not a normal shape of memory alloy, but a shape of memory alloy characterized by a pseudo-elastic effect,
okay,
where the critical temperature is lower than the environment temperature, because we haven't recovered the shape without heating.
Yes, I understand. Yes, it's very interesting, the condition of experiment. Thank you very much.
Thank you very much to you. Other questions? No one? So let's move to the other presentations. Oh, I recall another one, the not present authors, fracture behavior of reactor seal 20 magnesium moly nickel 55 in the transition temperature region by Dordevich, Petrovitsky, Sedmak, Kozak, and Samardzic. Sorry for my pronunciation. No. Another one is influence of the B material interface on the crack propagation through a thin protective layer by Malikova, Miarka, Beck, and Seitl. Please. Is there? You have to switch on the microphone. No? Okay. I move to the last presentation is structural assessment of a ladder frame chassis using finite element analysis, a designed construction referring to Ford AC Cobra by Majid, Laxono, Suryananto, and Prabowo.
Yes.
Sorry for my pronunciation.
Can you hear me?
Please. Please. Please, Adbul.
Yes. Okay, can you see it?
Perfectly.
Okay. Hello everyone. I am Imam Abdul Majid, student of Mechanical Engineering Department at 11 Maret University in Indonesia. I'm proud to be here to present my research about structural assessment of ladder frame chassis using finite element analysis, a design construction referring to AC Cobra. Yes, as we all know, Almost all activities carried out by people are related to use of transportation structure. Automotive chassis is a frame just like a skeletal, all with various machine parts. It gives strength and stability to the vehicle under different conditions. This research analysis of the design chassis referring to an AC Cobra car using finite element analysis technique. The applied material used for AC Cobra similar chassis is steel and is designed using a double-sided tube beam leather frame. The design using finite element simulation on the Autodesk Fusion 360 software, the specification and material properties of the chassis is described in Table 1 and Table 2. Then the boundary condition is defined in modeling, shown in Figure 3. The car chassis model is loaded by static forces from the car body and passengers. Load is 49,000 kilograms in vertical forces. The tail loading is shown in Figure 4. Analysis of the design car chassis referring to AC Cobra is carried out, aiming to find out how much displacement, stress strain, reaction force, and safety factor. In general, the chassis is safe enough to be used for sports car. The maximum displacement is 0.3359 millimeter with a 1.153 safety factor, and the maximum von Mises stress of the chassis is 264.4 megapascal. It means that the chassis can hold 4,900 Newton vertical load and still deform elastically and even under allowable material properties. Thank you for your attention during my presentation. Time I return to the moderator.
Thank you, Adbul. Any questions?
Yes, please. I have basically 9 questions.
Please,
Okay.
Mohammed.
Yes. Okay. Thank you. So first, why AC Cobra be the object of your research, and why it is important? Okay, that's all. Thank you.
Yes, thank you for your question. Here we only make a replica of the original chassis model of AC Cobra because the AC Cobra chassis has a simple leather frame chassis type. The leather frame chassis considered one of the oldest form of automotive or car chassis still used by most SUVs today. As its name implies, the leather chassis resemble a leather frame or leather shape having two longitudinal rails interlinked by several lateral and cross braces. I hope your question is answered, sir.
Thank you, Adbul. Any other questions? So, Adbul, I have just an advice for you. I see in this slide, in the number 2 stress strain contours, the third principal stress is 26.79. Okay, I think that this number is so much precious for simulation because you are estimate very small stress. Okay, I think is closer to 27 and megapascal and stop. Okay. And I have a question for you. How your model takes into account the difference of stiffness due to welded joints in the chassis or plastic deformation due to machinability of the components?
I'm sorry, sir. Let's repeat your question. Short question.
How do you take into account the presence of the welded joints in the chassis? As an homogeneous material, or you modelized the welding too?
Yes, in my research of the simulation, we are not in this research just statical load, yeah, and
Please, can you repeat slowly because I have a problem with the line. Did you take into account the joints?
sorry. In this research just statical load, and we are not considering welding connection in this chassis.
Okay.
The welding connection is negligible in this research.
Okay, thank you very much. This is another reason to reduce the precision of your numbers. Okay.
Yes.
So, any other questions? No one? So thanks to all the speakers. The session number 11 is closed. I remember you that the next session will start in an half past 4 in this link. Okay, thank you very much.
Thank you very much.
Later.
Thank you, Mr. Chairman.
See you later. Bye, Oleg. Bye, Noni.
Thank you very much.
All the best.
Hi, Noni.
Hi, Costanzo. How are you?
Fine, thanks. And you?
Fine. How is the conference going?
Yes, we are good. We are starting this last section for today.
Well,
And
I attended some sessions and everything seems to run very smoothly.
yes,
Perfect.
yes, all is going well, except this pandemic, but this is another question.
Yes, very difficult situation. Also
Yes.
here in Greece.
Yes, I think that we can start. It's 4:30. It's time.
It's time, Therma.
Yes. Okay. So, good evening, good afternoon. I am Costanzo Bellini from the University of Cassino, and I'm the chairman of this last section, last for today, but we will have other section on next Monday. And I will be the chair of this interesting section. We will have 12 speech from 4 out of 5 continents, so an international conference. And as usual within this conference, each speaker has about 10 minutes at his disposition, and as usual 2 minutes for a short report, of his work, and then 8 minutes for a debate with the other people present, both in presence in Turin and online. So we can start with the first work. The first speech is entitled "On the Assessment of Non-Metallic Inclusions" by Part 13 of API 579-1 PSME FFS 1 216. The authors are González Velázquez and Entezari from Mexico.
Yes. How are you, everyone?
Okay, you can share your screen if you want, if you have a presentation.
Let me share my presentation.
Okay. Okay, I can see your screen. The stage is yours.
Hello, everyone. First of all, thank you for providing opportunity for presentation our paper. I'm Ehsan Entezari. I'm from National Polytechnical Institute and Group of Pipeline Integrity Analysts, Mexico City, Mexico. I am going to present our presentation as on the assessment of non-metallic inclusion by Part 13 of API 579, Section 1, Asthma Fitness for Service Assistant, Section 1, 2016. As a definition and the main goal, the non-metallic inclusions are not considered as a defect by any code and standard. And this presentation introduced a new method for evaluation of non-metallic inclusion zones by considering them as a lamination. This presentation follows two goals. The goal one is level 1 and level 2 assessment of pressure vessel containing non-metallic inclusion zones by Part 13 of API standard And goal 2 is adopt the conservative fitness for service assistant procedure and criteria. As you can see here, you can see the photograph of assisted pressure vessel installed and operated in an oil production offshore facility in Mexico. And we did our research on this pressure vessel. And in order to find non-metallic inclusion zones, the phase array ultrasound testing and scan-C ultrasonic testing were done to find the non-metallic inclusion zones. And the non-metallic inclusion zones were detected in the hits of the pressure vessels here and here, and in the cylindrical section of this pressure vessel, this region and this region. And here you can see the photographic reports of zones of non-metallic inclusion. And as you can see, the blue spots are non-metallic inclusion here and here. And as you can see, these non-metallic inclusions are close to each other, and we can consider all non-metallic inclusions as a single non-metallic inclusion zones, and consider them as a lamination for evaluation then by part 13 of API standard. For assessment of non-metallic inclusion zones, first of all, we have to measure the dimension of non-metallic inclusion zones in circumferential and longitudinal direction, and also measuring the distance between non-metallic inclusion and the nearest other discontinuity, and measuring the distance between non-metallic inclusion and weld metal as a LSW. All of these parameters that you can see in this table are important parameters for assessment of non-metallic inclusion zones, and all of these parameters were measured for ultrasonic testing scan-C type. In this slide, you can see the level 1 and level 2 assessment of non-metallic inclusion zones. And as you can see, the level 1 assessment has been rejected because the dimension of non-metallic inclusion zones and also the height of non-metallic inclusion zones were rejected by this criteria, this and this, for all non-metallic inclusion zones, as you can see above this table. And also the distance between non-metallic inclusion zones and weld metal was rejected for these non-metallic inclusion zones, because these non-metallic inclusion zones are so close to the weld metal. And after rejection of the level 1 assessment, the level 2 assessment is required, and we did the level 2 assessment by stress analysis, and the level 2 assessment was done by commercial fracture mechanism application software to find the KIR and LR parameters. As you can see, LR and KIR parameters are as a function of the UTS, YS, and K1C. And this parameter helps us to plot the failure assessment diagram. And we found that all of these non-metallic inclusion zones are inside the failure assessment diagram. And because the reduced maximum working allowable pressure were more than the maximum allowable working pressure, the level 2 assessment has been accepted. And in this procedure, we found that there is a direct relationship between the LW, or the distance between non-metallic inclusions, and well metal and remaining strange factor. As I said these non-metallic inclusions are so close to the weld metal, and this decreased the remaining strange factor. As a conclusion, we found that the most important dimension for assessment are lamination size and spacing to the nearest weld joint, or LW parameter. And if possible, it is advisable to skip the level 1 assessment and directly perform the level 2 assessment, since it provides a less conservative assessment when the non-metallic inclusion zone is evaluated as a crack-like defect. And this paper provides a new method and horizon for evaluation of non-metallic inclusion zones, because the non-metallic inclusion zones are important site for hydrogen cracking, and the evaluation of these zones are important for pressure vessel and piping system. And finally, thank you for your attention. Okay. If you have a question, I'm ready to answer that.
Thank you. And are there any questions from the audience? Well, I have a couple of questions. You suggest switching from level 1 to level 2 that is less conservative compared to the former one. Well, can be this switch this switch be applied for all the cases, or only for vessel pipes, or for other cases? So, what do you think?
Yeah, absolutely, yes. Because for this type of inclusion, closely spaced non-metallic inclusions, all non-metallic inclusion is rejected for level 1 assessment because the LH parameter, the height of lamination, will be rejected for all type of non-metallic inclusion zones. And in this condition, we recommend that the level 1 assessment can be disregarded, and directly we can perform the level 2 assessment by the stress analysis and considering the lamination or non-metallic inclusion.
Sorry, I probably you or me lost the connection.
Let me explain again.
But very shortly, because the time is ending.
Okay, because in level 1 assessment, the LH, or the height of non-metallic inclusion, reject all type of non-metallic inclusion zones. We have to disregard the level 1 assessment and do the level 2 assessment by considering the lamination or non-metallic inclusion zones as a crack-like follow, and evaluation then by part 9 of API standard. And in this condition, we can consider the crack. We can consider the height of non-metallic inclusion zone as a crack length, and the crack tips is the maximum value of non-metallic size of non-metallic inclusion zone in circumferential and longitudinal direction.
Okay, thank you. Other questions? No. So, thank you, and for this interesting speech. And I can switch to the second presentation. The second presentation is entitled Assessment of a Designed Wheel Rim, a Convergent Study as a Calibration Reference for Structural Analysis using FEM. The authors are Sanjaya, Prabowo, Imaduddin, and Nordin. Are the authors with us?
Okay, thank you for the time.
Okay, so the stage is yours. You can share, okay. Now I can see your presentation.
Okay, hello everyone. My name is Yuana Sanjaya, mechanical student of 11 Maret University. Today I want to explain about my research. My research is about analysis mass convergence subjected to the rim wheel. So first, from the material properties, we know that the material of the rim wheel is steel alloy with the geometry as you can see as the picture, with the properties for Young modulus, stress of the von Mises and density, and this for the geometry. And it has a variation of mass size. And then the variation of mass size, it starts from 10 millimeter to 60 millimeter with multiplied by 5 millimeter. And then for the boundary condition and benchmark value, for boundary condition, wheel simulation has load of 21.3 kilonewton for each both holes, with the displacement for translational and rotational in XYZ direction is 0, and angular velocity for XZ direction is 0, and Y direction is 62.8 radian per second. For benchmark study, I cite from Karupusami for the benchmarking reference is used as a comparison, has a limit in the form of stress, von Mises, and displacement. In the benchmarking result of the rim wheel, it has displacement 2.34 multiplied by 10 power 5, and the von Mises stress is 240. And then from the simulation, we note that the conclusion, it has been proven that the mass size affects the result of the simulations. It can be seen from the different simulation results for its mass size, and the conclusion of, and number 2 is based off the result, error percentage still allows material that is simulated has the post result for the mass size of 10 millimeter, 15 millimeter, and 20 millimeter. For the error ratio of displacement, it has average of 0.122, and the error ratio of stress has average for 0.117, and from the coefficient error of variance, it can be result for the lower the value of variations, the more precise the estimate, and vice versa. Okay, thank you. That's my simple presentation about my research.
Okay, thank you too. And are there questions from the audience? Well, I have some questions. First of all, you have evaluated the influence of the mesh size on the results, but what about the time required by the calculator, computer, or workstation to complete the simulation? So, what can you say about the required time, the computing time?
Okay, for the first, I designed it using Fusion 360 and then the simulating static analysis using ANSYS static simulations, and it has 1 until 5 minute simulation time per each mesh size.
Sorry?
Padahal gue baru perawatan sekali loh. Oh, kalau perawatan lagi apa Bibi nggak tambah gerung-gerung?
Perhaps the sorry, perhaps there is someone that has his okay. Okay, so what about also there is a methodology. Can you define a methodology to choose the right mesh dimension, depending on also the simulation, to find good mesh sites?
From the meshes, first in the Karupusami for the benchmarking value, it has mesh size of default. And then from this, I thought it has improvement for the mesh size until it convergence. From the mesh size, I start to 10 until 60. That depends on my assumption of this is the closest result for the mesh size to benchmark study.
Okay, I see that there is a question perhaps from the audience. There is an hand-on from Noni.
Just a question. We know how the mesh size affects the results we obtain. I would like to ask if you plan to make an experiment or if you have any other data you can compare your results with. Thank you.
Okay, thank you, Noni, for the questions. From what I talked before is the data I use for the benchmark study is from the Karupusami journal in 2017. But from the experiment data, I haven't data yet from for the simulations. So I said for Karupusami for benchmark study.
It is also a numerical study, right?
Excuse me, can you repeat?
The benchmark study is a numerical study.
For the benchmark study, wait.
I mean the values shown in table 2 were obtained from ANSYS.
Yes, this is from ANSYS. I did a boundary condition with the same conditions, and then I compare the result for benchmark study and my study.
Okay, thank you.
Okay.
Okay, if there aren't some questions, we can switch to the next presentation. Okay. So, thank you, Ioana.
Okay, thank you, moderator, for the time.
Sorry for the pronunciation of your name and surname. And I can switch to the next one. That is mixed mode 1 and 2 fracture analysis for the various concrete types. The authors are Andrade Lizarro, Setl, and Miaka. It's a collaboration between the Czech Republic and Spain. So are the authors of this work with us? The work is mixed mode
first and second, fracture analysis of various concrete types. Andrade di Zarro, Seattle, and Miarca. No one is answering, so I go on to the fourth presentation that is entitled Optimization of Parameters on the Failure Stress Behavior of Strands using Takuji Method, presented by Gounia from the University of Medina. Is Anas Gounia with us? Yes.
Hello.
Hello. So if you want, you can share your screen. The screen is not shared, but if you want, you can. Okay, now it's starting the sharing. Okay, now I can see your screen. So the stage is yours.
Hello, Mr. Costanzo Bellini. I'm sorry for this late. Ladies and gentlemen, and thank you for watching my presentation. I am Anas Gouya from University of Science and Technology, Mohammedia, Morocco. Today, I will talk about optimization of parameters on the failure stress behavior of strands using Tagoshi method. I should begin with a motivation, following by the materials of work. After the analysis by Abacus, we'll have Tagoshi design results, and discussion will be the last part of this presentation. The steel core are used field of application. They can use it as reformation in heavy duty caused by inflation pressure, and the amount of the weight accord is a set of persistent steel wires assembled in on different layers.
Sorry to stop you, but the slideshow is on the first slide, so it's not running.
Can you repeat, please?
Okay, now is running. Now you are on the second slide.
Yeah. In this work, we focus on the analysis and the effects of design, manufacturing, and operating parameters of wire ropes on the failure stress behavior of central core strands of 19 multiply 7 wire ropes. We have chosen a 19 multiply 7 wire ropes using different types of material, copper, aluminum, and steel. The geometric model is imported into Abacus. Mesh, there are different formulation of elements in the finite element method. For this model, the elements used in the mesh are C3D8R. This type of element is defined as a linear brick with 8 nodes. Reduced integration time, increasement control for the discretization of the strand elements with the mesh pitch of the order of 2 millimeters. The number of meshes is equal to 39,403. This part contains the Tagoshi design. Our aim is to find the optimal conditions. We have choose young models within angle and diameter, of course, using their levels. And there is a table show the 27 tests using the Minitab software are without forgetting failure stress. Numerical analysis of the strand failure stress properties was performed on the 27 strand models with different configuration to maximize the failure stress. Considering the optician larger is better, we output the optimal conditions from the main effects plots of the SN ration. The optimal condition are Young model E equal 200 gigapascal and with an angle O equal 229.19 degree. And the last one, the diameter D equal 1.9 millimeters. The interaction of experiment DOE with the finite element method FEM and design is done to appreciate the effects of parameters such as material type, geometric shape within angle and their interaction on the mechanic behavior of cables. A Tagoshi experimental design to optimize the optimal parameters, the effects of the optimal conditions on the failure stress was studied. We varied 3 factors on 3 levels.
Sorry to stop you once again. I have to ask to you to go to the results to summarize your results and your conclusion, because the time at your disposition is only 10 minutes. Thank you.
Yes, the last one, sir.
Okay, thank you.
Okay, thank you, sir, for attention.
You can explain your conclusion if you want. You have enough time for conclusion if you want.
Okay, sir. First of all, I had choose the materials in this work because they are most using in this field. After we use geometry in the analysis using Katia. After that, we using Abacus for for analysis the cable. The optimal parameter is E3, B3, and C3. Is combination is used to validation test, and the simulation values of the first model are compared with the analytical values, and the error is 8.30%, which is reasonable in the field.
Okay, thank you. Are
Thank
there
you.
Are there questions from the audience? Okay, I have just a curiosity. So you are simulating a rope, and how was the friction among the strands and the wire taken into account in your simulation, if it was taken into account?
The number of strands, it's 7 multiply 19. The total is 133.
Okay,
According
there is a
the seven central core strands.
okay. So the friction among the strands was not considered in your simulation, isn't it?
I have forgotten. Sorry.
Okay, and another question. So you have considered the maximization of the maximum load of the fiber stress as the optimization target. And what about the manufacturing cost or the weight of the strength to weight ratio? So can they be optimized, or have you a solution for this?
Yes, we have choose and using this method not just to optimize the stress, but also the goal from this work to to lower the cost of the core.
Okay, thank you.
Thank you, sir.
Anas, and if there are no questions, I can call the next speaker.
Thank you, sir.
Yes, you're welcome. And the next speaker, I see him online, is Boris Fedulov from Russia, and his work is entitled Topology Optimization with Space Orientation of Reinforcement. The authors are Fedulov and Alexei. I see your presentation. You can start whenever you want with your short presentation.
About topology optimization. So topology optimization is a method to find the optimum structure. And this is an example. We usually minimize the compliance. So it means we maximize the stiffness of the structure. It's a more statement of problem for topology optimization. But what to do if we have additive technology like this? If we have printer that can put plastic and the continuous fibers simultaneously. It has freedom, and one more parameter is that we can choose the orientation of the our material, or how to place fibers. And in this case, we can add to our optimization task one more parameter, is angle orientation, and solve some problems. We implemented this idea into Abacus software. Some examples. So here, for example, is the bending beam, and you can see we have two fringes, density, and another one is angle orientation. So this is the three-dimensional example. There's another one. Okay, another one, something like brief. Here you can see we have two loads here. And here, for example, something more difficult. It's interesting that we have these transversal supports. Here, the two-dimensional example. Here, another one. Kind of brief. What is interesting that fibers always has orientation along structural elements that the topology optimization produce. We actually don't need this angle orientation finish, so we can be sure that it goes through the most loaded bars in a structure. Here's another example. It's applied moment. This is kind of more difficult one. We took something real. It is the pedal from the race car, and we did modeling. Here we have all contacts, and the convergence was very poor, but we did it, and we got this design, and finally we printed. We put the result into the program which was developed for this printer by company and and they finalize our geometry. They put somewhere pure plastics where we have small density of the material. This is how it looks. So here we have printer trajectories, how extruder will go through. And finally, we printed this. As you can see, here the white plastic. That means it is not enforced by fibers. And this is how it prints.
Okay.
And one more time, all steps here, how it works. And that's all. This is my favorite slide. Thank you.
Okay. Thank you for your work. And are there questions from the audience? I have some questions. So the proposed methodology that you presented for for this topology optimization has been validated. So, for example, the pedal that we have seen during the manufacturing process has been tested.
No, the pedal has. We didn't optimize it from strength point of view, so I think we can crash the whole car with the pedal. It's always strength. Because, we just wanted to see can we finish it or not using optimization and printing.
Mm-hmm. And the gain in terms of weight, have you evaluated the gain. So the improvement in terms of weight, because there is less material on the pedal.
Yes, we need to check. Good question, yeah. But it's very light now.
Ah, okay, so it's next step.
Yeah.
Well, so we can, if there are no questions from other people, we can go to the next one. So thank you, Boris.
Thank you very much.
I want to recall the previous authors. The work was mixed mode first and second mode flexure analysis of various concrete types. The authors are Andrea de Lizarro, Seitl, and Miarca from Czech Republic and Spain. Are they with us? I think I can go ahead with another work for now. So the next one is on the use of probabilistic fatigue life estimation in defining inspection intervals for railways axles, presented by Malor, Calvo, Luis Núñez, Rodriguez, and Landa Berea. I see that the presentation is already online. The presenter is Carlos Malor. Okay. Please unmute your microphone. And sorry for the pronunciation of your surname and name. I see that your microphone is muted.
Sorry. Good afternoon.
Okay. Sorry. Now the presentation is off.
Okay. I think I'm having problems with my screens now.
Before I saw it.
Can you see it now?
Okay. Now is it?
So good afternoon, everyone. First of all, I would like to thank you for organizing this event. My name is Carlos Mayor. I work in the Aragon Institute of Technology, ITEINNOVA, in Spain. And the presentation I submitted to the conference talks about the use of probabilistic fatigue life estimation in defining inspection intervals for railway axles. So briefly, I'm going to summarize that presentation. Then, first of all, a derailment of a freight train has dramatic consequences. And an example that you may sadly remember is this one here. A few years ago in Viareggio, in Italy. And that accident was investigated, and the cause was a fatigue crack growth in an axle, as you can see on the image on the right, induced by fatigue. So the goal of this work is to develop or to improve the current state-of-the-art methodologies in order to make those the safety of those axles safer. So briefly, the state-of-the-art nowadays basically considers the geometry, the loading conditions, the material properties, and from that data, we can calculate the expected lifespan estimation based, for example, in the well-known NASRO crack growth model, which is an updated version of the well-known Paris equation. And by doing so, we obtain the A versus N curves. That is the number of kilometers traveled or the lifetime calculation. And what I'm proposing is instead of using the previous deterministic calculation in order to set an inspection regime for those axles, I'm proposing to use a more complex probabilistic formulation, probabilistic computation of that lifespan, and I'm proposing that because of the amount of uncertainties that are related to the loading conditions, to the scatter of the material properties or the geometrical parameters. And briefly, what I'm doing here is I'm using the deterministic Nasr equation, and I am applying the full second order approach in order to make it a probabilistic model. And doing so, I am able to obtain a complete probability distribution. Instead of a single deterministic calculation, I obtain the complete probability. And that was correlated numerically compared with the Monte Carlo method, and it's just it's a model which is available. And I prepare a numerical example that is related to a railway axle of a freight train, and I assume an initial crack geometry, which is an unusual assumption in a damage tolerant assessment of railway axles. And directly going to the results, I'm able to obtain the complete probability distribution, and not only it is fitted by a simple normal or log normal distribution, I can also fit with a more precise distribution, in this case using the beta prime distribution. And by using that distribution, we consider a reliability percent which uses the prediction of in the lower tail of the distribution in order to obtain a conservative estimation. So by using the probabilistic method, we obtain a more conservative estimation than the deterministic one. And then we can use that conservative estimation in the state-of-the-art damage tolerance methodology in order to set or to calculate, to define an inspection interval. And for this particular example, we obtain a periodicity of 800,000 kilometers. So in the end, here, according to those results, it's recommended to inspect that axle every 800,000 kilometers using the usual ultrasonic non-destructive technique. And we can also know in the performance of that non-destructive method, we can calculate the associated cumulative probability of detection that I'm showing in the graph on the bottom right. So briefly, to conclude, only the 3 bullet points. First, we've applied the full second order approach in order to make the Nasr equation, which is deterministic, in order to make it probabilistic. We take advantage of those moments of time in order to fit a probability density function, in this case using the Pearson distribution family. And from that probabilistic results, we can merge them with the damage tolerance methodology in order to define better the interval inspections for railway maintenance. And that's all, really briefly, and I'm pleased to answer your questions.
Okay, thank you. Very interesting work. I used the same image that you have used for my course, my lesson on fatigue, the axle from Viareggio.
Oh, okay. And, I didn't see it.
Yes. Are there questions from the audience, from Turin or from the internet? If you want, you can use also the chat. Well, I have some questions. So there are several fatigue crack grow models at your disposition. Why did you choose the NASGRO one?
Well, in the short answer, in the bibliography related to fatigue in railway axles is the most common one. So that would be the short answer. And the longer one would be, well, it is very important to precisely characterize the first stages of the growth. And in that part, the most important parameter is the threshold parameter, and it is well described in the NASGRO model.
Okay. Other questions from the audience? I have another curiosity. If you have a very large variance of input data,
yeah,
this methodology is still working. So you can you apply it, and or there is a limit?
Well, I tested. Well, first of all, thank you for your questions.
You're welcome.
I have to say that yeah, this is a problem. Typically, those methods are less accurate the longer the input randomness is. But in this particular case, I've used, for example, talking about material scatter, I've ranged that input variability in a bigger range than the actual experimental variability, and I'm able to obtain good results. Here in this brief presentation, I've skipped the comparison with the Monte Carlo method, but we are talking about less than 8% invariance. So we can handle it.
Okay, thank you. And if there are no questions, other questions, I can switch to the next presentation. So thank you, Carlos.
Thank you, you're welcome.
And the next work is from Spain too. The title is Assessment of Notched PVC Tubular Beams Using the Theory of Critical Distance and the Finite Element Analysis. The authors are Sanchez, Quicero, and Arroyo from the University of Cantabria. I see Quicero.
Yeah, do you hear me?
Okay. Yes, I hear you, and I see your screen, so you can start
okay,
whenever you want.
Okay, hello everyone. Just very briefly, what we have done in this work is to provide some additional validation of the theory of critical distances in combination with finite element analysis for the analysis of, let's say, real structural components. In the last, I would say, 2 decades, there has been extensive validation of the theory of critical distances, especially on CT and single-edge notch bending specimens, but there are few results on real structural components. That's why we have analyzed 4 PVC tubes like the one you may see on the figure. With one of them was used to extract the tensile and fracture specimens and to characterize the material, tensile properties, fracture properties, and critical distance. And the other 3 were notched here in the encastrate section with different diameters, different notch radii, etc. And once we had the material characterized and the critical distance determined, we used a finite element model of the tubes and the notch and apply the external load till the point method condition was fulfilled, deriving then the corresponding load bearing capacity. And what you can see here is the comparison between our estimations and the experimental results, where you can see that the results are quite, I would say, decent, within the mass plus minus 20% of accuracy, which is acceptable in fracture mechanics. And that's all, pretty much. Thank you very much.
Okay, thank you. And are there questions from the audience? Well, I have two curiosities.
Okay.
So you have applied your approach to PVC and a tubular shape that is quite simple, even if there is a notch. But this approach can be extended to other type of shapes or other type of material?
Yeah, in fact, we also have this kind of validation of aluminum alloy tubes. And in literature, you may find similar applications on complex geometries. I think Lucas Susmel has, and Taylor, I think it's Taylor. They have some analysis in quite complex geometries. But I mean, step by step, being honest, if you look in literature, there are very few results. So although we trust on the theory of critical distances quite a lot because it has been widely validated on laboratory specimens, the results on real components are really scarce. So we need to work on it quite a lot yet.
Yes. And so another curiosity, in the FEM model, have you simulated the concrete block, or which is the boundary condition to block the tube?
Yeah, no. We just blocked that extreme of the So no, the concrete was not simulated.
Okay, so only the pipe with the nodes.
Yeah.
Okay. So other questions from or curiosities from the audience? So no other questions. I think that you have another slideshow, another presentation.
Yeah.
Okay, so see you later.
See you. Thank you.
You're welcome. We can go to the next one. I see on the screen the next one. So the title is on the thermal response of lutetium aluminum garnet activated by cerium single crystal, and the authors are Saksakis, Linardatos, Karpeteas, Kalinvas, Ninos, Bakas, Avdas, Fontos, Kardanakis, Balais, and Mikhail. Sorry for the pronunciation of your surnames. And this work comes from Greece. So I think that the presenter is Saksaki.
That is correct.
Okay, so I can see your screen, so you can start.
Thank you very much, Mr. Bellini. At this point, I would like to thank very much the organization committee for inviting us to present our research work in the IGF26. Our research work has to do with the thermal response of some crystal scintillators. And actually, the aim of our research was to further expand the current knowledge of scintillators and to investigate the influence of temperature on the luminescence output of single crystal scintillators in harsh environments. Single crystal scintillators are used to be used in harsh environments like geophysical detectors for deep geology boreholes, or non-destructive testing of pipelines in oil and gas industry, space and marine exploration, nuclear reactor monitoring, radiation chemistry, and other corresponding research fields. So what we did at this research project, we used the lutetium aluminium garnet, which was examined and compared to previously published data for cadmium tungstate and calcium fluoride doped with europium single crystals. So the project was designed like the crystals were exposed to X-rays on a general medical Mirate tube with a rotating tungsten anode. We used KVPs ranging from 50 to 130 KVPs. And what we actually did is that we placed at this point the crystal, and then the X-rays ran through the crystal. The crystal was generating light, and the light was collected by this integrating sphere, which is connected to this photomultiplier. So the light, the emitted light from the crystal was collected to this integrating sphere, and the photomultiplier produced an electrical signal which was fed to this electrometer to be digitized and then fed to a PC so that we can use the data and produce the results. So the single crystal which was put at the entrance of this integrating sphere was heated with a heating gun, and the temperature was accurately measured with an infrared laser thermometer. So the single crystal was heated, and then the temperature was monitored through this digital thermometer, the infrared digital thermometer. That crystal's temperature was increased up to 128 degrees of Celsius, and it was found actually that in this temperature range, which is usually used for logging detectors, all the literature was actually in this temperature range, approximately from below 0 to 200 degrees of Celsius. So we exposed this insulator to excessive heating. We didn't notice any cracking. And in this figure, what it shows is that the light that was actually generated by the crystal was fed in the integrating sphere, and this is actually, this plateau is the usable area of the crystal, which actually shows that even with the very small temperature up to the highest 120 degrees, and this crystal does not show to have any temperature fatigue and has this kind of plateau. So the signal which is produced, the electrical signal which comes from the luminescence of the crystal, remains almost unchanged. So comparing to the other two single crystals that we had studied previously, we can clearly see with this green line that this crystal, the lutetium aluminium garnet, is much better and more stable within this temperature range compared to the cadmium tungstate and the calcium fluoride doped with europium single crystals. So this is, we are very happy to see that this crystal remains actually unchanged in this temperature area, because this means that we can use this as a detector to this harsh environment, given that its luminescence is not actually affected almost at all by this temperature increase. So what we have shown in this research is that even though the other single crystals can provide characteristics that could be very nice to have in harsh environments. The luminescence efficiency of these crystals, and I'm talking about the cadmium tungstate as well as the calcium fluoride doped with europium crystals, show a decrease, a luminescence decrease, which is close to 80% up to 120 degrees of Celsius. And on the contrary, the lutetium aluminium garnet activated by cerium single crystal remains unchanged, which is very nice characteristic to have when it comes to measure these measure temperatures and use this as a probe in harsh environments. So its thermal stability is the very nice characteristic that was proven through this research. That was all. Thank you very much for attending. If there is any question, I would be more than happy to answer.
Okay, thank you, Dr. Sakis. And are there any questions? From the audience? No. So I have a question. Mm-hmm. You have said in the presentation that I saw on the internet that an excessive heat flow or an X-ray flow can damage the crystal, can result in the cracking of the crystal. And so what are the limits and what are the restrictions in practical applications?
Okay,
and if there are solutions to this problem.
Through the literature, we have found out that Custom Green in publication in 2019 and Compluta et al. At 2015, they used such crystals in their experiments, and they found out that excessive heating or excessive X-ray flux can actually damage the crystal and have small crackings inside the material, or even in quite excessive heating, even a general crack of the crystal. To be honest, we didn't have any, we didn't experience anything like that in our range of temperatures. And as far as I know, even at the temperature that are close to 1,500 of Kelvin, they don't have this cracking. Actually, the cracking, the limitation of the cracking could be related to how much time you expose this crystal to these temperatures or to this X-ray flux. So it's a matter more of time that you keep this crystal under this condition, rather than reaching a value that could possibly crack it, because it's quite different for each crystal. And as far as I know, there is no cracking referenced at least up to 1,500 degrees of Kelvin. So it's actually a matter of time and
of rate. Heating rate. It's a matter of heating rate. So
yeah. Okay. So it's really, we didn't have any kind of this experience in our experiments, and I think it's pretty difficult to have it. But when you are designing a detector that could be used, for example, in space exploration or something like that, where radiation would be pretty high, as much as temperature, then you might take under consideration that you need to test this crystal under these extreme conditions, because you don't want this to fail when you are in space. So you need to take this under consideration while you are testing this material. But in our case, and for our experiments in this range of temperatures, we didn't have any kind of such experience. And I think we are far away from something like that, since as far as I know, that this crystal has been tested for 1,500 degrees of Kelvin and didn't crack. So we are far below this.
Mm-hmm. Okay. Okay. Thank you. Nice answer.
Thank you.
Other questions from the audience? I have just another curiosity, and you mentioned during the presentation the date of purchasing of this crystal, but is a perishable material, or it's just a case that you mentioned the date?
Actually, the materials were the crystals were bought from a company that actually sells them, and you have also the chance to place the order, or how you want the crystal to be in terms of dimensions, and how you want to be the surface being prepared. If you want them to be clear, like all crystals, or if you want them to be faded or something like that. So we didn't made the crystals. The crystals were bought from a company. They were purchased.
So the day of purchasing is not so important. It is not a perishable material.
No, it's not. You buy the crystal the way you want it to fit your experiment. So you set the dimensions, and you set the clarity you want to have, and everything like that.
Okay, thank you. And if the questions are ended, I can switch to the next presentation.
Thank you very much, Mr. Bellini.
Welcome. So the next work is entitled Considerations on the Thermoelastic Effect in Proximity of Crack Tips on Titanium and Aluminium. A new formulation. These works, the authors of these works are Palumbo, De Finis, Di Carolo, and Gaglietti from Polytechnic of Bari, Italy. Is one of the authors with us. Palumbo, De Finis, Di Carolo, or Gaglietti? So no one is answering. I switch to the next one. Then I will recall them. The next work is entitled Embrittlement by Trump Element and Determination of its Allowable Content for Electric Furnace Steel. The authors are Hayashi, Kawabata, Yoshimoto, and Yamamoto from the University of Tokyo in Japan. So, is one of, okay. So, Saki Hayashi, sorry for the pronunciation, is presenting. I can see your screen, so you can start whenever you want.
Yes, I'm sorry if my English is poor to understand.
Don't worry.
My title is Embrittlement by Trump Element and Determination of its Allowable Content for Electric Furnace Steels. There are two ways to make steel materials, the blast furnace and electric furnace. And compared to the blast furnace steels, the electric furnace steels can contain impurities like tin or copper, but emits less carbon dioxide as the graph below shows. So, to promote a low carbon society, electric arc furnace is important. However, the ratio of electric furnace materials is not large. The reason why electric furnace steels are not used is electric furnace steels contain impurities like tin or copper. And this graph shows steels which contain tin can become embrittled when tempered in a certain temperature range. And in the field of large structures, a large heat input is used for welding joints. In the welding, temper embrittlement can occur in the heat-affected zone. So electric furnace steels contain tin have rarely been applied to the field of large and high-grade structures. So goal of our research is increase of the share of electric furnace steels in crude steel production. So we decided to investigate allowable contents of tin that prevent toughness loss during welding. So we conducted fracture tests on specimens with different amounts of tin and different heat treatment conditions. We used specimens with these chemical compositions. And the amount specimens with three different amounts of tin, 0.01 and 0.1 and 0.2, and heat treatment conditions. These heat treatment conditions was applied as shown in this figure. And toughness was evaluated by performing 3-point bending tests and calculating the critical quality CTOD, one of the fracture toughness parameters. And ductile brittle transition temperatures were calculated by using critical quality CTOD. The lower the transition temperature, the better the toughness. So the smaller the delta T, the better the toughness. And this is the this graph shows temper embrittlement occurred in steels with not less than 0.1% tin, whereas the change of 0.01 tin steel is flat. And as the holding time increases, the toughness improves regardless of the steel grade. This is probably due to the fact that the effect of tempering on toughness is greater than the effect of temper embrittlement. And first, we investigate fractography. Previous studies shows that tin segregates at grain boundaries and causes intergranular fracture. However, when we conducted fractography, unlike the previous results, only cleavage fractures were observed. And we considered about why did transgranular fracture occur. Brittle fracture, and the form of fracture is determined by which is more likely to occur. So first, we consider the likelihood of fracture before tin segregation. basically, in matrix or base plate, these locations are piled up at the grain boundaries, and this can be the starting of a fracture. In addition, intergranular fracture is more likely to occur. On the other hand, in the weird heat-affected zone, CZ, these locations are piled up not only grain boundaries but also around precipitate. So these locations are so the probability of the origin of fracture within the grain increase. And before tempering, the transgranular fracture may be more likely to occur in HAZ than in matrix. And after tin segregation, tin segregates at grain boundaries, and tin weakens the bonding strength of grain boundaries, and cracks are more likely to propagate along grain boundaries than within grains. So intergranular fracture likelihoods increase more, and totally intergranular fracture occurs. On the other hand, in CZ, tin segregates at precipitate interface in addition. So tin weakens interfaces, and cracks are more likely to occur both around grain boundaries and within grains. So both fracture likelihoods increase and transgranular fracture occurs. This is my conclusion. Thank you for listening.
Thank you. And are there questions from the people online and also in presence in Turin? So, could you give more details about the CTOD tests, in particular the testing temperature, if is it possible?
The reason of why we choose CTOD as a fracture parameter.
So testing speed, the distance between the supports.
Three bending tests are relatively easy to conduct for us like students. So
no matter if you don't have informations about it. Probably the former slide. So this is the CTOD test. And as concerned the dimension of the specimen, which are the dimensions? Because the dimensions can influence the thermal inertia of your specimen. So the thermal inertia during the tempering cycle. You are applying a tempering cycle of 5 seconds in one of the case. So are there problem with this thermal inertia?
sorry, I
I see that there is a
thermal cycle, a tempering cycle of lasting only 5 seconds. And which are the specimen dimensions? Because you have to deal with the thermal inertia of your specimen. So have you encountered the problems? Have you noted something strange with this time, with this very short time?
So, excuse me, I am Kawabata. I am a co-author of this study.
Yes, of course.
So, let me confirm your question. You are asking this heat treatment is accurate or not? So
yes, it's a curiosity because 5 seconds seems to be a very short time.
Okay. We simulate this heat treatment for welding. So you consider very short heat input welding. So holding time is very short. So 5 seconds is enough time. But consider about high heat input welding. So the holding time is very long. So we here we conducted heat treatment as very small specimen and induction heating, simulated HSD method, and then we conducted a CDOD test. So also we conducted with very small 10 millimeter and 10 millimeter section.
Okay.
Right.
Okay. Thank you so much. And if there are no questions from the other people, I can switch to the next work. So thank you so much. And the next work is entitled High Temperature Wear Behavior of Aluminium Magnesium Scandium alloy produced by laser powered bed fusion. The authors are Abrami, Montesano, Tocci, Pola, Gelfi from the University of Brescia.
Good evening. Can you see my presentation?
Yes,
Do you hear me?
Yes, of course, you can start.
So thank you very much for the presentation. My name is Beatrice Abrami, and I am a PhD student from the University of Brescia. And my work regards high temperature wear behavior of scalm alloy, which is an aluminum magnesium alloy reinforced with scandium and zirconium, produced by laser powder bed fusion, which is an additive manufacturing technique used for to manufacture metallic components. So in order to investigate the wear behavior of scalm alloy, we performed a pin on disc test for a total distance of 500 meters and under 4 different temperatures, so room temperature, 100, 150, and 200 Celsius degrees. We then evaluated the coefficient of friction and the wear rate. The wear rate was calculated both after 100 meters of riding distance and after 500 meters. In fact, every test was stopped also at 100 meters in order to evaluate an intermediate condition. So after test, Vickers microhardness was performed in order to monitor the microstructure evolution after test, in particular after the 6-7 hours of high temperature maintaining. And we also performed SEM analysis in order to better understand the damage mechanism, these at the two distances, so both for 100 meters and 500 meters of distance. The conclusions, the main conclusion are summarized in the next two slides. So first, we can see from the plot on the left that for every temperature, the steady state condition is reached after 500 meters of sliding distance. And moreover, the COF steady value increases with temperature, as can be seen on in the second part of the plot. About the wear rate after 500 meters reaches an almost equal value for every temperature investigated. And this can be seen by observing the orange histograms in the plot on the right. And this means that there are no temperature effects on the wear rate when the steady state conditions are achieved. So after 500 meters of sliding distance. About the wear mechanism, the tribo-oxidative wear mechanism is the one, the predominant one occurring. But anyway, at higher temperature, we have also the adhesion, as can be seen from the table on the left that summarize every test condition. And we have that at 500 meters of sliding distance for the higher temperatures, we have also the presence of iron oxide together with the aluminum oxide, which derives from the counterpart. About the microstructure, we can say that the Skarmalloy microstructure is stable with temperature, as can be seen from the plot on the right. That plot the microhardness as function of the temperature. We can see that there are no significant variation, and so the microstructure is stable, and the precipitates do not go into solution even after the high temperature maintaining. So the changes in the behavior of Skarmalloy at high temperature are due to phenomena and mechanisms that are promoted by the temperature rather than its microstructural variations. And so we can say that the alloy is suitable for wear application in temperature. Thank you for the attention.
Thank you too. And are there questions from the audience? Did you use the optimal manufacturing parameters from the manufacturer of the powder or of the machine, I suppose?
Yes, let me open the other presentation.
Yes, I have a question. How can the manufacturing parameters influence the wear behavior?
The study, for this particular study, we didn't focus the attention on the building parameter, but I think that with the final density of the components, so the level of porosity, are directly affected by the processing parameter of the process, and so they are an important they are important factor to consider it, I think. But in this study, we, as you previously said, we have started from an already manufactured material. Yes.
So the default parameter. Yes.
This is the annealing treatment is at 325 Celsius degrees for 4 hours. Is the one that improve at the best the material property. So this was done to the annealing treatment in for our specimens.
So another question: the wear tests were carried out on a surface that was parallel to the building direction, I think. So if you consider another...
no, the building direction, sorry,
the building direction, I think, is the zeta. In this figure is the zeta direction, isn't it?
Yeah. Yes, is the building direction, but the these tests were performed on the larger area. So the perpendicular.
Okay, so the surface that is the lateral surface in this image.
Yes.
And if you consider the upper surface, for example, that is a surface perpendicular to the building direction, so the surface finishing is different, because if you consider the upper surface is usually it is smoother. So what can you expect from this surface?
Before the test, we have also reached a specific ruggedness by polishing the surface. But in any case, if the surface is more what is the is more is less uniform, we will have a more irregular behavior at the wear
because
test.
I think that the texture of the lateral surface is different compared to that of the upper surface. So usually is
yes, because if I okay. So, for example, these are micrographs in the cross section. So, in the building direction, so Z, and with the additive manufacturing technique, we have this structure which consists in the overlap of successive layers and these melt pools that are the microstructural solidification structure of the alloy. So in the other direction, we have other textures. So the answer is yes. The behavior changes also in these cases. But anyway, also we have to say that this alloy, rather than others, has a structure which is less anisotropy respected than other alloys. So this is also to keep in mind.
Thank you for this exhaustive answer.
Thank you.
And are there other questions? I think not. Okay. Thank you.
Thank you.
And I want to recall the previous work whose authors were absent. I make a tentative. So are there Andreade Lizzarro, Stanislav Setl, and or Petr Miarka. The work is entitled Mixed Mode 1 or 2 Fracture Analysis of Various Concrete Types. No? Next call for the other work is entitled Considerations on the Thermoelastic Effects in Proximity of Crack Tips on Titanium and Aluminium, a new formulation. The authors are Palumbo, De Finis, Ticarolo, Galietti from Polytechnic of Bari. No. And so we can, I saw that Sergio Chichero is ready in the chat. So the second work is entitled Some Thoughts About the Application of the Master Cure Methodology to Ferritic Steels Containing Notches. The authors are Sergio Chichero and Sergio Arieta. So the stage is yours.
Okay, thank you very much. Thank you very much for those who are still here with us late evening on Friday. And thank you for the chairman for this fantastic job. I guess that many of you are aware about the master curve methodology, which is used to characterize the fractal toughness of periodic steels within the ductile to brittle transition zone. It actually follows this weakest link statistics, and then can be modelized by using a 3-parameter Weibull distribution, on which this lowercase b is the shape parameter, this k min is the location parameter, and k0 is the scale parameter. These are the 3 parameters to be defined for periodic steels. Then Kim Ballin in the 80s and 90s defined which values should we take for these parameters. And 5 years ago or so, we published a couple of papers applying the master curve to ferritic steels in notched conditions, obtaining the corresponding, instead of using the reference temperature, we obtain the apparent reference temperature, which of course is dependent on the material and also on the notch radius. Well, we in fact received a little bit of criticism from Kim Ballin, explaining that we should better justify the use of these Weibull parameters used in cracks. We should better justify these parameters also in notch, and that's what we have been doing in the last months, and what we want to present here. Summarizing, here is a little bit of analysis concerning B, the shape parameter, on which for a given set of experimental results, for a given temperature and a given notch radius, you just have to rank the results and provide this kind of analysis and obtaining the corresponding slope. And this is the value of B and the number of tests here, and the representation is like as follows. You can see here the results obtained for the different set of experimental results, and these are the confidence bands used by Ballin, and it pretty much fit the confidence bands, or at least in the same way as it was done for cracks. Concerning the location parameter, if you look at the physical binning, it means that you require this 20 megapascals square root of meter to obtain cleavage factor. Below this value, it's not possible to have cleavage factor on structural steels. And of course, if you have this value for in cracked conditions, you at least need this value in notched conditions. So we may use it as a conservative assumption. Concerning the scale parameter, this expression is the one derived by Walling in the 90s, and it is purely experimental. It's a fitting equation, and these are our results for notches. And you can see that, well, it reasonably fits the equation, so we can use then the shape parameter, the location parameter, and the shape parameter in notched conditions as well. Then there are other aspects of the master curve that are also have been conveniently justified in the paper. For example, the KJC limit, above which it is not clear that we have small scale yielding conditions and high constraint condition, etc. And in the procedure structural integrity paper, we will explain it in detail. With all this, if we once the use of these parameters is justified, we may use exactly the same equations for the apparent fractal toughness. That's why we have an N notch here. and the reference temperature is the apparent reference temperature. But the experimental procedure to obtain this parameter, which at the end is the only parameter that we need, is exactly the same as that used for cracks. And of course, we have a reference, an apparent reference temperature for a given notch radius. With all these are all the experimental results we have on 4 different structural steels with different notch radii from 0.15 millimeters up to 2 millimeters in some cases, and how the experimental results fit the master curve quite reasonably. So with all this, as the main conclusions, we justify the use of master curve in notched conditions, and the experimental results validate the use of this tool in such conditions, in notched conditions. And that's all. I'm open to any question about this.
Thank you. And questions from the present? So I have a couple of curiosity. You have applied this methodology, this approach to common seal, more or less common seal. Yeah. Also high strength, quite high strength steel. But can this approach be extended to other materials, a very ductile material or very fragile, yeah. So from aluminum to?
No. It's just, I mean, the master curve is for structural steels, but ferritic steels from low grades, you can see here, for example, 275, up to, I think that the limit of the yield stress is somehow, it's like 900 megapascal, so all the range. Mm-hmm. I mean, it's ferritic steels, but not necessarily with ferritic microstructure. Original ferritic microstructure, but it may be magnetic or whatever.
And other kind of metals?
No.
So no. If you,
of course, you need a ductile to brittle transition zone. So aluminum wouldn't be the case. It's not. I mean, it's just for
steel.
Yeah.
Okay. And another curiosity. So the comparing the graph for the crack and for the notch, even if they are on different material, the variance of the K parameter seems to be lower for the notch compared to that for the crack. So
you mean this scatter?
This scatter with that one for the notch.
Yeah.
So they seems to be not similar. So for the crack, there is a for the notch there is a lower scattering.
Yeah.
It seems.
Well,
can you explain this?
I didn't think about it, to be honest, but I mean, the scatter is also quite high here. Maybe, yeah, it's a bit lower. I don't know. At the moment, by the time of fracture, let's say that the plastic zone should be larger in the case of notched specimens, and that's maybe why the scatter is lower. But this is compensated by the sensoring process that you have to complete during the application of the master curve. So I don't have a definite answer on this, to be honest. Okay. But you can see that there is quite a lot of scatter also here.
Yes, but it seems that in the case of the crack is larger. Maybe it's only a case that you get these results.
Yeah.
So, other questions from the present? No. So, thank you.
Thank you very much.
And you're welcome. So, last call for the
the remaining speech. The first one is a mixed mode 1 or 2 fracture analysis of various concrete types. The authors are Andrea De Lizarro, Seattle, and Miarka from Czech Republic and Spain that are not present. And the last call also for considerations on the thermoelastic effect in proximity of crack tips on titanium and aluminium, a new formulation. The authors are Palumbo, De Finis, Di Carolo, and Galietti from Polytechnic of Bari in Italy. Are they with us? No. And I think that the last this presentation was the last one for this section. So we ended in time, and this is the last presentation for today, the last section for today. There will be other 4 sections for on next Monday, and so I can give the word, the stage to the main direction in Turin, if there is anyone, or I can say have a nice weekend to you, to the present, and see you on next Monday for the last 4, I guess, 4 sections. Yes, there are 4 sections on next Monday. So the last day of May.
Thank you very much for all participants. Bye.
Okay, thank you very much. Bye bye.
Bye.
See you on Monday.
Thank you so
Bye.
much. Bye.
Ok, see you Vittorio.
Ciao, ciao.
Ciao.